weighing 390 tons fully loaded. This is one of the biggest heavy-lift transport planes in the world. The Antonov 124 Ruslan. Its mission is to fly cargo weighing up to 120 tons, thousands of kilometers, to any place on Earth.
Failure is not an option.
What design innovations allow engineers to build an aircraft this large? And what technologies make the 124 capable of swallowing loads whole? We unlock the engineering secrets that make this aircraft the king of heavy lifters. From its 4 mega-sized thrust-boosting engines to a tough skeleton forged from light but super strong materials, to reveal what it takes to build the ultimate megaplane. Kourou, in French Guiana, South America. Home to the European Spaceport. Here, the European Space Agency operates 3 launch pads. Up to 12 rockets blast off from this facility every year. They carry into orbit telecommunication, weather, and observation satellites, critical for 21st century life back on Earth. French Guiana's equatorial position makes it the perfect place from which to launch satellites. The Earth's surface spins fastest at the equator. This higher speed slingshots rockets into space using less fuel. But the satellites they carry aren't built here. Each one must be shipped to Kourou ahead of its launch. This high-resolution Earth observation satellite, costing 100 million euros, is the next craft bound for space. It's under construction at this factory in Toulouse, France, nearly 6,800 kilometers away. Workers assemble the satellite in this dust-free, temperature-controlled laboratory. Project manager Sophie Lay needs the satellite in Kourou within the next 48 hours to prepare it for launch.
It's a tiny schedule, so we need to have a very direct transport from Toulouse to French Guiana, and a lot of things can go wrong. We have to be very careful.
The satellite ships in a special sealed container, like this one, that stops dust and changes in temperature from damaging its sensitive components. Hauling such a box to French Guiana by truck and then ship could take weeks and increase the chance of a malfunction. Sophie's best option is to fly the satellite to the launch site in a cargo plane. Transporting a box this large is a huge challenge. It measures 4.5 meters wide, 4.2 meters tall, and 8.8 meters long. Together with the satellite support equipment, the total payload weighs 42 tons. To get the cargo to Kourou, Sophie calls in this: the Antonov 124 Ruslan. This heavy-lift aircraft is 69 meters long. Its wings span the length of more than 3 tennis courts. And inside, it has a huge 1,000 cubic meter cargo bay. This mega plane transports more supersized commercial cargo than almost any other aircraft. The plane is built with innovative technology hidden under the hood to carry the world's heaviest air freight. A lightweight fuselage strong enough to carry 120 tons of cargo. An ingenious kneeling mechanism to help load the biggest freight. Powerful and efficient engines to propel the plane further on a single tank of fuel. All these elements combine to make the Antonov 124 Ruslan, the ultimate cargo plane. 4 p.m. Toulouse Airport, France. The 124's flight crew prepare the aircraft for takeoff. Loadmaster Oleksiy Pavishko and his team must ensure the plane is in top condition to fly.
Main purpose of our group is maintenance this aircraft before takeoff, after takeoff, all period when the aircraft is flying.
Ahead lies a grueling mission. First, the crew must load the 42-ton satellite cargo. They must then fly the 124 non-stop nearly 6,800 kilometers across the Atlantic Ocean to reach Cayenne, French Guiana, 10 hours after leaving France. Next, the crew must unload the cargo onto trucks. These transport the satellite 1 hour northwest to Kourou, where engineers will prepare it for launch. The Antonov's unique feature is its 1,000 cubic meter cargo bay. It's 150 cubic meters bigger than those of many rival heavy lifters and large enough to carry 50 family-sized cars. To create this much room, the Antonov's designers placed the aircraft's 73-meter-long wings on top of the fuselage. But building an aircraft body strong enough to handle the load is a huge engineering challenge. The wings of most commercial aircraft connect in a wing box in the center of the fuselage. This strong box supports the aircraft's body. By positioning the wing box above the fuselage, an aircraft gains a larger cargo hold, but risks catastrophic structural failure. The Antonov's wings, 4 engines, and fuel tanks weigh over 150 tons. This huge load could squash and damage the plane's fuselage. And if the aircraft gets airborne, the dead weight of a 120-ton cargo could then rip the plane apart. To solve the problem, engineers must strengthen the fuselage directly beneath the 124's wings. On traditional aircraft, engineers rivet together thin strips of aluminium to build tough support frames. But the size and weight of the 124 could overstress the rivet line. So here, at the Antonov aircraft factory in Kiev, Ukraine, Vitaly Zatsakovny's team builds lightweight mega components designed for maximum strength. Workers fabricate supersized load-bearing parts for the Antonov from these solid blocks of aerospace aluminium called billets. This special alloy is as strong as steel, but 3 times lighter.
Аналогов, наверное, таким заготовкам нету. Алюминий прочный, легкий и долговечный.
High-powered, computer-controlled water jet cutters carve each 25 centimeter thick, 5 meter long billet into rough shapes. Next, special machines cut away the excess metal according to a precise design to make each component even lighter. The finished piece is a perfect balance between strength and weight.
Особенности цеха состоят в том, что оборудование по своим размерам позволяет изготавливать детали практически любых размеров, учитывая, так сказать, особенности и размеры Руслана.
Workers bolt together up to 4 cut billets to make a special load-bearing structure called a frame. Engineers install 6 primary reinforcing frames directly beneath the 124's wings. Each frame can support the weight of over 600 tons. That's more than double the combined weight of the aircraft's wings, engines, and full fuel tanks. For extra strength when carrying heavy cargo, engineers install another 117 secondary frames. They encase this skeleton with aluminium panels, machined with integrated reinforcing ridges. These panels spread the load forces across the aircraft. At Toulouse Airport, Alexei's team finishes prepping the 124. The monster plane is ready to be loaded up with its precious satellite. What technology makes it possible for this aircraft to literally swallow its cargo whole? And what is the secret that keeps this plane airborne for thousands of miles without needing to refuel? In Toulouse, France, ground crew prepare the Antonov 124 cargo plane to fly a 100 million euro satellite nearly 6,800 kilometers to Kourou Spaceport in French Guiana. At the satellite factory across town, a team lifts the 10-ton sealed box containing the precious cargo onto the back of a low loader. It will deliver the box to Toulouse Airport in just 4 hours' time. The pressure is on the 124's crew to make sure the aircraft is ready. This super plane is designed to fly the heaviest, bulkiest loads to anywhere on the planet, with or without an airport. Military vehicles, industrial equipment, even other aircraft. The 124 can carry and deliver anything weighing up to 120 tons, so long as it fits. The Ruslan's rear doors swing open to load cargoes up to 3.8 meters tall and 6.4 meters wide through the back of the plane. But the satellite shipping container measures over 4 meters tall. The challenge for the Antonov team is how to get this oversized box onto the plane. The answer is to swallow it. Literally.
Now we prepare to the loading. We must make next operation. We must open the nose.
The 124 has a second huge loading door. 3 giant hinges connect the 1-ton nose section to the top of the plane's fuselage. A pair of hydraulic rams pushes the nose forwards. In less than 60 seconds, the front of the Antonov completely opens up to reveal a doorway 6.4 meters wide and 4.4 meters tall. Just big enough to thread the satellite box through. The next step, lowering the Antonov's onboard ramp. The 124's opening is 3 meters above the ground. Deployed from this height, the gradient of the 9-meter-long ramp is 20 degrees. Pushing the 4-meter-tall satellite box up this incline creates a challenge for the crew. The top of the box could hit the roof of the Antonov's cargo bay. If it clears the gap, the 8.8-meter-long box will reach its tipping point. There's a risk it could crash down onto the cargo bay floor and damage the fragile satellite inside. Logistics manager Joran Mark must ensure the delicate satellite makes it to Kourou in one piece.
It's one of the most sensitive cargo we can move because all the equipment installed in the satellite is very sensitive to the shocks, to the modification of the temperature outside. So it's always a challenge to move it.
The team members can't afford to damage the satellite as they load it. This will cancel the rocket launch and cost potentially hundreds of millions of euros.
Failure is not an option.
At the satellite factory across town from the airport, workers secure the oversized box to the low loader. The convoy departs. It will arrive at the airport in just 1 hour. The box must not slam into the ceiling of the cargo bay or crash down onto the floor during loading. So engineers equip this super plane with an innovation that should make the box slot straight in. This factory in Ukraine is where workers service Antonov's 7-strong fleet of 124s. Here, mechanics strip down the massive frames of these aircraft to run regular checks under the hood. A critical inspection reveals this machine's secret for loading tall, heavy cargo in through the nose. Above the undercarriage sits a pair of hydraulic motors. The oil inside the motors is pressurized to 210 bar. That's 100 times higher than the pressure of a car tire. The hydraulic system helps the Antonov kneel down. The motors power 2 1.7-meter long, high-tensile steel screws attached to the front landing gear. When they twist, they rotate the landing gear forwards, jacking down to the ground 180 tons of aircraft. The process lowers the Antonov's opening to just 1.2 meters above the ground and reduces the ramp's angle to just 8 degrees. This should stop the tall box from hitting the cargo bay ceiling as the team loads it. In Toulouse, Loadmaster Alexei initiates the kneeling system. Gas turbine auxiliary power units pressurize the hydraulics. The screws begin to turn. The huge aircraft bows down and rests its 180-ton empty weight on sturdy outrigger feet. Alexei's team unfolds the internal ramp. Next, his mechanics add an extension ramp to make the angle with the cargo bay floor even shallower. As night falls, the convoy carrying the satellite arrives at the airport. Logistics manager Yoran takes over responsibility for the cargo. This 70-ton crane lifts the sealed box from the low loader onto the ramp.
I will be happy when the container will be loaded in the aircraft.
A winch fixed inside the 124 slowly pulls the satellite into the hold.
You can lose everything in a minute.
Now comes the moment of truth. Will the box fit?
Stop, 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 stop.
The clearance between the top of the container and the ceiling of the aircraft is only a few centimeters. The box just slips through the gap.
The distance 2 centimeters, it's not problem for the loading. I think it's very well.
The loadmaster was really efficient. I told him my congratulations because he did a really good job for the preparation of the aircraft.
The crew loads the 3 smaller boxes containing the equipment needed to ready the satellite for launch. Next, they use super strong steel chains to secure the cargo to the 124's titanium floor. The megaplane is loaded up and ready to go. Yoran calls Sophie Lay at the spaceport in Kourou.
Hi, Sophie, Yoran.
Hello, Yoran.
Everything's on schedule.
Okay, 10 hours and you will be in Cayenne.
See you in Cayenne tomorrow morning.
Very good. Thank you. Bye.
Ahead lies the Antonov's next challenge, flying non-stop across nearly 6,800 kilometers of open ocean. What engineering secret allows this super heavy 124 to speed through the skies without refueling en route? And what technology keeps the plane stable in the most extreme weather conditions? 5 a.m., Toulouse Airport, France. Flight officers prepare the supersized Antonov 124 cargo plane for takeoff. In its hold, a special temperature-controlled box carrying a 100 million euro satellite, bound for Kourou Spaceport in French Guiana. To get there, the 124 must fly nearly 6,800 kilometers across the Atlantic Ocean. Navigator Anatoly Abdullayev must keep the aircraft on course for its entire journey.
My job is to find the right way from one origin airport to destination. We should fly very accurate and about altitude and longitude and latitude.
The Antonov must carry enough fuel to complete the trip in one go. There is nowhere to fill up over the Atlantic.
This can't refuel in the air, only on the ground.
Building engines that are both powerful enough to thrust the 124 forwards and efficient enough to fly long distances is a huge engineering challenge. The Antonov's 4 engines produce more thrust than 7 F-16 fighter jets. They push the monster plane through the sky at 850 kilometers per hour. But the more powerful the jet engines, the more fuel they consume. A regular jet engine burns fuel up to 2,000 degrees centigrade. Exhaust gases blast the aircraft forwards and spin turbines connected to compressors at the front of the engine. These force more air into the combustion chamber, making the fuel burn even hotter. This standard system makes jet aircraft fast and also very thirsty. The 124 could run out of fuel way before reaching French Guiana if fitted with regular jet engines. This aircraft needs a super-efficient propulsion system in order to reach Cayenne Airport on 1 tank of fuel. Antonov's planes undergo regular checks here at this maintenance hangar in Ukraine to ensure all their 124's engines are in full working order. Chief Engine Mechanic Pavlo Kieshner oversees the operation. Big overhauls strip away the engine's outer casings to reveal their secret for maximum efficiency. First, the Antonov's designers attach a 2.4-meter diameter fan to the front of each engine. Each fan weighs nearly 3 tons.
Двигатель D18, двухконтурный, турбовентиляторный. Они доработанные, уже ресурс побольше и надежность побольше. Несмотря на то, что вентилятор очень тяжелый, он вращается на подшипниках, вращается очень.
Next, they wrap each engine in a symmetrical ducting system. The ducting encases almost the full length of each 5-meter-long jet. The Antonov's designers then install an extra turbine at the back of the engine. This turns a shaft connected to the giant fan. It's made from 33 angled blades of titanium. The spinning fan pushes more air into the engine's compressors. It also blows air at high speed through the ducting and out the back of the engine. By doing this, the system nearly doubles the thrust of a regular engine for the same fuel consumption, to give the Antonov's engines more bang for their buck. In Toulouse, the ground crew finishes pumping 150,000 liters of jet fuel into 13 compartments inside the 124's wings. This is more than enough for the journey to Cayenne, thanks to the megaplane's super-efficient engines.
No one aircraft can carry more fuel than we. The most long flight of this aircraft, from takeoff until landing, more than 25 hours.
It's time to go. The 4 monster turbofan engines fire up. The massive aircraft taxis to the runway.
Antonov 275, ready for takeoff, runway 08.
Antonov 2753, runway 08, cleared for takeoff, window 11.
The pilot accelerates the 124 to 260 kilometers per hour. The giant plane takes to the skies. The precious satellite is now en route to French Guiana. Up ahead, new challenges await the 124 and its crew. How does this superplane stay airborne during dangerous turbulence? And what secret technology stops it from skidding off the runway when it lands? 9,500 meters above the Atlantic Ocean, the Antonov 124 megaplane carries a €100 million satellite bound for French Guiana. The spacecraft ships in a special dust-proof and temperature-controlled box to protect it from damage. The box must be delivered to project manager Sophie Lay and sealed inside this clean room at the European Space Center in Kourou within 5 hours to prepare it for launch.
It's very important that the satellite arrive very fast here in a clean room to minimize the risk of failure of the container. So we want that fastest time to put the satellite in a safe area.
On board the 124, logistics manager Joran checks the status of the box's air conditioning every half hour. The temperature must remain within strict limits. Changes in temperature can damage the satellite's sensitive components.
We have placed a cable with the sensor on the satellite container in the cargo cabin. We are supposed to be at 22 degrees Celsius, so we are 22.2. Oh, that's perfect.
The Antonov is 500 kilometers from French Guiana's international airport in Cayenne. This part of the plane's journey is the most treacherous. Here, close to the equator, wet, warm air from the Atlantic creates towering thunderclouds and powerful storms. The 124's crew carefully monitors the danger posed by this changeable, often violent weather.
We study the weather conditions around the route using the radar system. Turbulence is a big problem for aircraft, very dangerous for aircraft and cargo.
Extreme winds buffeting the Antonov could shake the satellite box, break its seal, and let in damaging dust and moisture. It's critical this mega plane maintains smooth and stable flight for the rest of the way to Cayenne. But giant aircraft in extreme winds can be vulnerable to developing a dangerous type of roll. A strong wind gust tips an aircraft to one side. Wing drag then skews its yaw, the angle it flies forward through the air. Pilots can reduce speed to stop the roll and maintain stable flight. But the design of a super-huge high-wing aircraft can increase the impact of strong winds. The 124 has a low center of mass and a high lift point, so when wind tips and twists the aircraft, it soon swings back the other way. The plane sways back and forth like a pendulum. This motion greatly intensifies the stresses on the aircraft. In the worst-case scenario, extreme winds blasting a giant plane could shake loose its heavy cargo. An unsecured load inside the Antonov could have deadly consequences. April 2013. This Boeing 747 cargo plane suddenly stalls and crashes to the ground shortly after takeoff. All 7 crew members on board are killed. The investigation reveals the 80-ton cargo inside the plane broke loose. The aircraft's balance pivoted backwards, and the 747 fell from the sky. To complete its mission, it's critical the 124 beats extreme winds. At the Antonov maintenance hangar in Ukraine, mechanics run vital tests on the system designed to keep the 124 stable in the most dangerous weather conditions. All aircraft use their wings ailerons and their tails elevators and rudder to maneuver through the air. These control surfaces on this super-huge cargo plane are super-sized. The Antonov's 4 ailerons weigh a total of 290 kilograms. This giant plane needs actuators fed by hydraulics, pressurized to 214 kilograms per square centimeter to move control surfaces this heavy. It rests on the shoulders of Alexei Skrinik to make sure that this system works perfectly.
Ну, так как да, давление большое, довольно-таки большие риски утечки гидрожидкости, все. Поэтому мы контролируем все и стараемся, чтобы не допустить утечек, ничего, все.
Alexei's team tests every joint on the 4,100 meters of hydraulic pipe woven into the 124's mighty frame.
Могу сказать, гарантия техника. Утечек нет. Самолет обслужен, осмотрен, все хорошо. И самолет будет летать еще очень долго, дай бог.
The Antonov's secret for beating strong winds is linking its control surfaces to an ingenious automatic steering system. A pair of sensors mounted inside the Antonov's fuselage measures the aircraft's roll and yaw. The sensors send this data to the computer controlling the aircraft's flight surfaces. When wind rolls and twists the plane, the computer moves the rudder and elevators to counteract the motion and maneuvers the aircraft back to level flight. This system works independently of the pilot and keeps the Antonov stable in the most challenging weather conditions. With the system engaged, the 124 carves through the powerful winds close to the equator. The satellite is safe and secure in the hold. The Antonov is now just 300 kilometers from Cayenne Airport. But new challenges lie ahead. What is the engineering secret that brings a 124 weighing up to 330 tons to a full stop on the runway? And what is the technology that allows the crew to unload cargo super fast? 200 kilometers off the South American coast, the Antonov 124 megaplane prepares for landing at Cayenne Airport, French Guiana. On board, 42 tons of fragile satellite equipment, bound for the European Space Center in Kourou. At the airport, project manager Sophie Lay awaits the plane's arrival. Her team is gearing up to load the satellite onto this truck and transport it to the Space Center 70 kilometers northwest.
I'm very excited to see that everything is ready, the flight is coming, all the vehicles are here, so it's great.
3,000 meters in the air, the pilots lock in the 124's approach. the aircraft must follow a precise path and speed to the runway. 59% of all aviation accidents happen during the landing sequence. The heavier the load a plane carries, the faster it must go to stay in the air, and the faster its speed at touchdown. The 124 must maintain a steady 280 kilometers per hour to remain airborne. That's 50 kilometers per hour faster than the average passenger jet. Stopping a supersized aircraft traveling at this speed on the runway is a big engineering challenge. On the brakes of a traditional aircraft, calipers grip a solid steel disc on the vehicle's wheel axle. When the calipers engage, the friction turns the axle's kinetic or movement energy into heat. The system is perfect for stopping light, slow-moving vehicles. The 330-ton Antonov touches down with a kinetic energy of over 230 Formula One cars, traveling at full speed. Turning this amount of energy into heat could soften the steel brake discs so much that they cannot stop the Antonov hurtling off the runway. The dense jungle surrounding Cayenne's 3,200-meter-long landing strip adds to the pressure. Coming off the runway could end in disaster. Moscow, 2012. Car dashcam footage captures the moment a Tupolev Tu-204 aircraft slams into a road at 190 kilometers per hour. 5 crew members on board the plane lose their lives. Investigators conclude the jet overran the runway when its brakes failed during landing. To prevent an accident like this, the 124's designers build in a superheat-resistant braking system to bring this mega plane to a stop. Here at Antonov's maintenance hangar, a critical inspection of this aircraft's landing gear reveals the machine's secret for shedding heat. Chief Mechanic Petro Danilov leads the maintenance team. The 124 has 20 1.3-meter diameter wheels at the rear. Each 160-kilo wheel is attached to a 1.4-meter long axle. Each axle has 5 brake discs. Vents on the wheel hub channel air onto the discs.
Тормоз колеса охлаждаем. Вот эти вот отверстия — это для охлаждения тормоза. Здесь стоит вентилятор. Там стоят термопары, он меряет температуру есть и выдается на прибор в кабину экипажа.
The 124's designers build in a special material to cool the brakes even more. They swap conventional steel brakes for carbon discs. Carbon can absorb far more heat energy than steel. The material won't melt under extreme braking. They stack 5 discs onto each of the axles holding the Antonov's 20 rear wheels. Spreading the heat energy produced by friction over more discs makes the system even more resilient. The brakes pulse on and off to prevent tires from locking up and skidding on wet runways, and bring an Antonov weighing up to 330 tons to a full stop. At Cayenne Airport, the mighty cargo plane comes into view.
Here it is. A big, big plane. Lot of noise.
It's time for the Antonov's brakes to do their job. The plane's 20 rear wheels touch down. The brakes heat up to 550 degrees centigrade as their calipers grip carbon discs to slow the plane. the giant 124 decelerates and taxis towards the terminal.
Every time I see that plane, I'm very excited. It's the final of a satellite adventure, so it's great.
Now comes the Antonov's final challenge. Unload the satellite onto the waiting convoy as fast as possible. What special technology allows this plane to shift bulky cargo quickly? And will the Antonov's precious delivery make it to the Space Center in one piece? At Cayenne Airport in French Guiana, the Antonov 124's crew prepares to unload the megaplane's precious satellite cargo onto waiting vehicles. The satellite must reach this clean room at the European Spaceport, 70 kilometers away in Kourou.
We have scheduled a specific planning in order to be sure that everything will be on time, and the crane is already here. We plan that in 2 hours we'll have the satellite container offload.
The operation must run like clockwork in order to get the satellite to the clean room within the next 3 hours. The first challenge for Loadmaster Alexei and his team is to move the lighter boxes carrying the satellite support equipment through the plane's rear doors. Using a forklift to shuttle the boxes individually from the cargo hold to the convoy will take too much time. The plane needs a way to transfer the boxes directly onto the waiting trucks. Maintenance checks at the Antonov hangar in Ukraine reveal the 124's secret for super-fast unloading. 2 overhead gantry cranes travel along 47-meter ceiling-mounted rails that run the full length of the cargo bay. Each crane is equipped with a pair of 3-kilowatt electric winches. Working together, the 4 winches can lift up to 30 tons. At Cayenne Airport, the first convoy truck reverses into position beneath the Antonov's tail. The crane overhangs the tail section with the rear doors open. The winch cables extend over 7 meters to the ground. This allows the plane to unload from its cargo bay straight onto the back of a truck. Alexei's team lowers the support equipment boxes one by one.
This operation continues one container approximately 5-7 minutes. It's very easy and I think not problem.
Moving the support equipment takes 1 hour. The next challenge, unload the 10-ton satellite box from the front of the plane. This mega aircraft once again flips up its nose and kneels on the ground. Alexei deploys the 124's built-in ramp. His team constructs the ramp extension. Another 3-kilowatt winch holds the box's weight as the crew guides it down the ramp. A 20-meter tall crane lifts the precious delivery onto the back of a low loader. It's mission accomplished for Alexei and his team.
It's very good. Our job is finished.
Logistics manager Yoran hands over the satellite to Sophie.
Hi Sophie, how are you?
Fine.
At this stage, the temperature we can read is 21.5. So that's fine, everything's all right.
Very good.
36 hours, our job is complete. Successfully. Happy. We'll have a good shower and a good rest.
The the satellite convoy hits the road. It arrives at the European spaceport, right on schedule. Technicians guide the box into a large airlock outside the center's clean room.
I'm very happy now that the satellite is arrived. It's the end of a story of 2 years of manufacturing, and the real operation of the satellite will start.
Over the next 4 weeks, scientists test and fuel the satellite before they load it into a 50-meter tall Ariane 5 rocket.
3, 2, unité. Top, allumage moteur Vulcain.
6 weeks after delivery, the satellite blasts into space. It will map the Earth from 200 kilometers above the surface for the next 20 years. The Antonov 124 Ruslan is bigger and carries heavier cargo than almost all other transport planes in the world. Built into its mighty frame is a series of ingenious inventions that make it the pinnacle of megalift plane design. Super strong and light components keep the fuselage rock solid. Giant jack screws kneel the plane to swallow monster loads whole. Thrust-boosting turbofan engines push the plane through the sky with maximum efficiency. Gyroscopes and super-pressurized hydraulics keep the aircraft steady in the strongest winds. Carbon disc brakes bring this monster to a complete stop on the runway. This giant aircraft carries the biggest, bulkiest air freight, further than almost all its rivals. The Antonov 124 Ruslan is built to be the ultimate. Stretching 3.4 kilometers across the St. Lawrence River, this is Canada's newest and toughest crossing, the Samuel de Champlain Bridge. With 3 months to go before it opens, engineers are locked in a race against time.
The clock is ticking. We're now in the final push.
What technologies make it strong enough to handle 60 million vehicles a year? And how does its design beat extreme winter weather?
This bridge has to be built tough in order to survive.
We unlock the engineering secrets that make this one of the most advanced bridges in North America. From its aerodynamic profile that stands up to the strongest winds, to a skeleton forged from super strong corrosion-resistant materials, to reveal what it takes to build the ultimate super bridge. Montreal, Canada. The nation's second largest city is a major hub for business and commerce. Montreal's success depends on its big bridges spanning the St. Lawrence River. They must move people and goods between the city, the rest of Canada, and the US. But building and maintaining big infrastructure in this part of North America is a huge engineering challenge. Over 12 months, Montreal's climate fluctuates wildly. In summer, temperatures can soar to a scorching 35 degrees centigrade. In winter, the mercury can plummet to -30. Fast-moving ice flows pack the St. Lawrence River, and freezing winds batter the city. To keep the city connected and moving in all weathers, engineers in Montreal are building this. The Samuel de Champlain Bridge. It spans 3.4 kilometers and costs over 4 billion Canadian dollars. The bridge is built using innovative technology, baked into its mighty structure to stand up to everything Mother Nature throws at it. Ingenious cables stop monster chunks of ice crashing onto cars and pedestrians. A deck structure that stays rock solid in the strongest winds. Expanding joints stop the bridge cracking up as the temperature changes. An ingenious drainage system flushes away corrosive salty water before it destroys concrete and steel. All these elements combine to make the new Samuel de Champlain the ultimate bridge. Construction work starts on the bridge in 2015. Engineers sink 37 sets of pillars, called piers, into the land and the St. Lawrence riverbed. Then they lay a steel platform on top of the piers. Next, they use giant floating cranes to place 9,600 concrete deck slabs. Today, this elite team work around the clock to complete construction and prepare the bridge for its opening in just 3 months' time. Once finished, this critical artery must carry 60 million vehicles and $20 billion worth of cargo each year. Stay open 24/7 in all weathers and survive for at least 125 years. The lifespan the Canadian government specifies for new critical bridges. Chief Engineer Guy Maillard leads a team in charge of the Herculean task of building this super bridge.
There's daily stresses on us, the entire team, to do whatever we can to get the bridge open in time. Because this bridge had to last for 125 years, it had to be built tough and resilient.
The stakes couldn't be higher for Guy and his team. Next door to the construction site is a big reminder of what will happen if they fail. In 1962, Montreal opened the first Champlain Bridge over the St. Lawrence River. It was expected to last for a century. But within 30 years, the bridge started to crumble. Now, after 5 decades in service, it needs round-the-clock monitoring and costly maintenance. Alex Chemenier is part of the team tasked with keeping the old bridge operational until the new one is complete.
To give an idea of how much these repairs have cost over the past few years, since 2014, approximately $300 million has been invested into the bridge. So we're looking at approximately $50 million to $60 million a year being put into the bridge just to ensure that it stays strong and it stays standing until the new bridge opens.
Along the length of the bridge, broken concrete exposes rusted rebar beneath. Engineers call this damage spalling.
Here we have some typical damages that we see across the bridge. We have some spalling, we have some exposed rebar. Typically, when the damages get a lot worse than this, we'll then intervene and do some patches to the concrete.
The cause of the spalling is the crucial chemical Montreal uses to keep the city's roads ice-free. Ever since the 1960s, the city covers its roads and bridges with salt, 130,000 tons of it every year. Salt is an effective way to melt ice, but it destroys concrete structures. When de-icing salts melt away snow, they dissolve into the liquid water and can trickle down the side of the bridge. Over time, this salty water seeps through the concrete and contacts the steel rebar inside. The salt water contains chloride ions. These react with the steel, causing it to rust and expand. Eventually, the bridge is so cracked and damaged that large chunks begin to break away. Left unchecked, the bridge's steel skeleton will become so corroded that the entire structure could collapse. The challenge for Guy and his team is to make the new Samuel de Champlain Bridge 100% salt-proof. To solve the problem, they must completely rethink the very fabric of this bridge.
In planning the new bridge, we really learned from the old bridge, and we were quite prescriptive in the type of materials to ensure that the bridge would perform well over its intended 125-year design life.
They choose to build the skeleton of the bridge from stainless steel rebar. This chromium-enhanced metal is 10 times more resistant to corrosion than traditional steel. Marcel Martineau's team then encases this skeleton in the ultimate protective concrete layer.
We have to ensure over 125 years that no corrosion will start on the rebar. That's the main challenge. The type of mix we're using for the deck, it's impervious concrete to ensure that the chloride ion won't go to the rebar and that start corrosion.
Engineers combine stainless steel rebar and corrosion-resistant concrete to produce the bridge's 9,600 deck slabs. Installing them onto the bridge structure takes 22 weeks. Today, Marcel's expert team races to fill the stitches between the slabs with more concrete. Its mix contains less water. This makes it denser than traditional concrete. Workers use special machines to eliminate air pockets to guarantee the concrete's salt-proof qualities.
The placing and the finishing of the concrete is as important as the mix itself. It's not done properly. At the end, the result, we won't achieve the 125 years life expectancy.
This section of roadway is just one small part of an ingenious drainage system. The bridge's designers engineer the structure like a giant sink to reduce the concrete's exposure to corrosive salt. The shape and angle of the deck's camber directs water towards drains sited along the edge of the roadway. Water flows into an intricate system of pipes up to 60 centimeters wide that run through the structure and down its pier legs. The pipes release the salty water a meter above the waterline. This reduces the amount of concrete exposed to the corrosive solution. Workers spray every square centimeter of set concrete with a synthetic resin to protect the bridge even more. This waterproof membrane is part of a layered system designed specifically to prevent the damage salt causes.
To ensure that we won't have corrosion on this bridge, we start with a good drainage system. We then have a thick layer of asphalt. We then have a waterproofing membrane. We then have high-performance concrete, which is much more resistant to salt penetration. And then we have the stainless steel rebar. And the old bridge had none of these. So I can say in conclusion, there's no way that salt is going to corrode the steel on this bridge.
The super bridge is now immune to the damaging effects of road salt. But this megastructure must withstand more climatic extremes to last 125 years. What technology protects it from Montreal's huge seasonal temperature fluctuations? And what is this bridge's secret for beating destructive winds? In Montreal, the new Samuel de Champlain Bridge opens in 3 months' time. It must be robust enough to serve the city every day for a minimum of 125 years. If engineers get its construction wrong, this new bridge could suffer the same fate as its crumbling older neighbor. One of the biggest challenges facing the new bridge's engineers is building a structure that copes with Montreal's huge temperature range. In summer here, the mercury can top 35 degrees centigrade. In winter, the temperature can plummet to -30.
It's important to keep in mind what 125 years means. In fact, the structure will be solicited by thermal variations in temperature, and these will be repeated every day for the next 125 years. So you really have to look at each individual component, understand how it's going to behave under that extended design life, and then design it accordingly.
Montreal's weather cycle will have a big impact on the city's new bridge. Almost all the bridge's components expand when they heat up and shrink when they cool. Individually, these variations in size are tiny, but combined along a 3.4-kilometer-long bridge, the difference can be huge. As Montreal freezes in the winter and warms in the summer, the bridge can change length by up to 3 meters over the year. If engineers ignore these fluctuations, the bridge's deck could buckle as it expands or crack as it contracts. To solve the problem, designers build 8 gaps into each of the bridge's 2 road decks. Each gap is up to 1.6 meters wide. These create space for the bridge to expand into. The gaps stop the structure from cracking up, but make it impossible for vehicles to pass. The solution is these ingenious expansion joints. They're designed to both fill the gaps and let the bridge flex. Intensive factory tests ensure each joint can withstand extreme temperature changes throughout the year. Today, project manager Alexis Lauzon oversees the final joint installation.
An expansion joint is an important part of a bridge to make sure that the bridge can move freely throughout the seasons. This expansion joint will take a lot of abuse throughout the years.
Alexis' crew installs 8 expansion joints into both of the bridge's road decks. The sides of each joint attach to the ends of 2 road sections. As the bridge expands or contracts, the joint's strips, up to 20 meters wide, move along rails. They react to the bridge's lateral and vertical movements. Buffers ensure the joint's metal strips remain evenly spaced as they move. And spring bearings beneath the strips distribute the load of vehicles through the bridge's concrete structure. Alexis' team swings into action. With 3 months to go before the bridge opens, they're under intense pressure.
The expansion joint that we're going to see today is quite heavy and quite big. We have a 16-meter piece that weighs around 16 tons. The workers need to be really meticulous because any wrong movement could be fatal. Actually, it could damage the bridge. It could also damage the expansion joints, and there's a lot of workers around the lifting process.
A mighty crane lowers the huge 16-ton joint into position. The team removes some steel obstructing the gap. Then the joint slots in perfectly. Expansion joints stop the bridge's decks from breaking up as temperature variations make them stretch and shrink. But the bridge's changing shape presents additional engineering challenges for this team. 6 of the huge deck sections attached to pier legs sunk deep into the St. Lawrence riverbed. These sections could break the joins to their legs as they expand and contract. And there's another problem. Montreal sits in an active seismic zone. Over the next 125 years, the city will experience at least one major ground movement. When it happens, there's a real risk the bridge will sustain catastrophic damage.
If the structure were not flexible under a seismic event, it would transfer tremendous forces because the structure would be much more rigid, which could potentially severely damage the piers.
Engineers install bearings that allow the deck to slip across its legs and stop the bridge from breaking apart.
The bridge rests on these bearings. These bearings allow the bridge to move. And I've just made a measurement. I can see that the structure has moved. When we go from hot temperature to cold temperature, about 7 centimeters since it was set in place by the marks that are left on the stainless steel plate.
Free to move and flex, the new Samuel de Champlain Bridge is ready to beat extreme temperature fluctuations and any future earthquakes. The engineers' next challenge is to make sure that this mega bridge can combat devastating winds and stand firm when hit by an onslaught of river ice. In Montreal, the new Samuel de Champlain Bridge must open in 3 months' time, ready to serve the city for at least 125 years. The bridge has 6 lanes to carry more than 1 million vehicles every week. But this mega crossing accommodates more than just cars and trucks. On one side is a pedestrian walkway and cycle path. A rail line will run down the center, directly into Montreal's central station. The bridge must be a massive 60 meters wide to accommodate all these elements. But in Montreal, size makes you a big target for a powerful force of nature. Winds in the St. Lawrence River Valley can reach speeds in excess of 100 kilometers per hour. To make the bridge super tough, engineers space its pier legs just 84 meters apart. This short length reduces the distance each deck section must span and bolsters the bridge against fast-moving air pushing on its massive structure. But one crucial part of the bridge needs a different method of support. Bridge piers cannot obstruct the 145-meter wide shipping canal running parallel to the river. To span it, engineers must suspend a critical 240-meter long section of the bridge. 30 cables attached to the 170-meter tall tower take the load. This leaves the shipping canal beneath the bridge unobstructed by piers. But suspending sections of bridge deck from cables makes them vulnerable to strong winds. The structure of some bridges forces air faster over the top of their decks than underneath it. This creates an area of high pressure beneath the bridge. Just like an aircraft wing, the deck can lift up, stressing the bridge's joints and damaging its deck. Every time the wind blows, there's a risk the new Champlain Bridge will suffer damage.
The bridge in the Montreal environment has to be aerodynamically stable in order to ensure that the bridge will not oscillate unexpectedly under intense winds.
Engineers deploy an innovative solution to eliminate the danger. They design gaps between the bridge's road decks and rail line. These gaps vent and disrupt the fast-moving air, preventing high pressure from lifting the bridge and damaging its deck. On paper, the bridge looks ready to withstand the dangers created by strong winds. But wind presents another engineering challenge for a cable-stay bridge.
By their very nature, cable-stayed bridges or suspension bridges tend to be very flexible, and so the interaction with the wind becomes very important.
As history proves, build a bridge that's too flexible, and wind will tear it apart. November 1940. Tacoma Narrows Bridge, Washington State. 4 months after opening, 65 km/h winds cause the bridge to twist and sway. The movements become so violent, the bridge breaks apart and collapses. The cause is a then little understood phenomena called aeroelastic flutter. Suspension bridges twist fast-moving air into mini whirlwinds that pull at the bridge deck. The shape and weight of most bridges means these vortices cause only a slight movement. But the Tacoma Narrows Bridge contains a critical flaw. Due to its narrow, lightweight deck, the vortices cause greater movement. Sustained winds make the bridge wobble and oscillate. The twisting eventually becomes so violent that the bridge collapses. To make sure the new Champlain Bridge doesn't suffer the same fate, engineers must test its design under every wind condition before construction.
You cannot really predict how well the bridge will be performing until you undergo some very intensive wind modeling to make sure that the bridge will respond correctly under wind loading.
Engineers enlist the help of aerodynamics expert Dr. Peter King. His team at Western University, Ontario, build a scaled-down bridge model costing 70,000 Canadian dollars. They test it in a wind tunnel to predict how the full-scale new Champlain Bridge will behave.
The model is a complete dynamic replica of the bridge, so it has the right mass properties, the right stiffness properties, and replicates all of the dynamic motions of the bridge. The model is at a geometric scale of 1 to 150, which has a velocity scaling of about 12 to 1. So that means everything that you see in the wind tunnel is happening about 12 times faster than it would in real life.
The model withstands simulated wind speeds of up to 180 km/h coming from different directions. That's 3 times faster than the wind that destroyed the Tacoma Narrows Bridge. To improve the new bridge's aerodynamics even more, engineers modify the sides of its backspan. This is the part of the suspended bridge that counterbalances the section crossing the shipping canal parallel to the river. They hope this adjustment will stop the bridge from shaking itself apart.
Here in the main span, we have a solid pedestrian barrier on the leading and trailing edges, whereas in the backspan, it's completely open and allows the wind to go straight through.
This tiny modification does the trick. The different barriers disrupt the wind flow over the bridge and reduce the pull on the deck. There's no danger the full-scale bridge will twist itself to destruction. The bridge can beat wind. But there's still more Mother Nature can throw its way. How will the bridge defend itself from concrete smashing ice flows? And what smart technology stops big chunks of ice falling from the bridge and crushing cars below? In Montreal, the new Samuel de Champlain Bridge opens in just a few months' time. It must be ready to serve the city every day for 125 years. The minimum lifespan the Canadian government specifies for new, critical infrastructure. Workers battle freezing temperatures to get the bridge finished on time.
In our goal to open the bridge in June, the clock is ticking. We're now in the final push.
This super bridge must survive over a century of brutal Canadian winters and the yearly onslaught of powerful ice flows.
Montreal is subject to winter freezing, where the temperature can go down to -40. This will mean that the river will freeze over. It can freeze up to 0.9 meters thick. This ice breaks up. It will generate large flows of ice that will impact the piers.
Blocks of ice can inflict critical damage to big structures that stand in their way. The current in the St. Lawrence River accelerates ice up to speeds of 4 kilometers per hour. A flow traveling this fast, measuring 45 meters across and 1 meter deep, grinds at the pier legs with the same force as the weight of 10 trucks. Cracking and eroding the concrete. This footage from the 1960s shows that ice flows on the St. Lawrence River have always been a problem. Just 2 years after the opening of the old Champlain Bridge in 1962, Montreal builds another huge span across the St. Lawrence. This massive structure is not a traffic crossing. It's the first line of defense to protect Montreal's bridges and shoreline. It's an ice-breaking megastructure.
In the winter, you'll have large ice flows which will build upstream, and then as they flow downstream towards Champlain Bridge, they will impact the icebreaker structure, and the columns of the structure will cleave these ice flows into smaller pieces of ice, and these are less damaging.
Even with a dedicated icebreaker, the old Champlain Bridge, 300 meters downstream, is covered in scars sustained in battles with the ice. Alex's vigilant team must react fast to keep the crumbling structure standing.
On our piers, we actually have steel lining just at the water level to ensure that when ice does hit the piers, that the concrete itself is protected. But over time, sometimes the steel lining disintegrates with the water and concrete can be affected. We do rapidly intervene to reinstall that steel liner in order to ensure that the structure remains intact.
This old icebreaker has only a limited lifespan. City engineers plan to decommission the structure in the future. For most of its life, the new bridge must face the ice onslaught alone. For the bridge to survive, it needs the strongest concrete legs of any structure across the St. Lawrence. Concrete is a mix of water, sand, gravel, and cement. Increasing the ratio of cement to water raises the concrete's density and makes it super tough. Engineers then add a secret ingredient that changes the concrete's chemistry to make it even stronger. At the atomic level, when cement mixes with water, the reaction creates calcium silica hydrate, which bonds the concrete mix together. But the same reaction also produces other particles that disrupt the bonds, forming weak points in the concrete. When engineers add a chemical called silica fume, it reacts with the disruptive particles, turning them into more calcium silica hydrate, making the overall structure stronger than ordinary concrete. In 2015, construction work on the bridge's piers begins. Engineers pour the pier bases on land and let them set solid. Then they use a floating foundation installer to sink 38 bases into the riverbed of the mighty St. Lawrence.
The mix used for the pier leg is the strongest mix I use in my 30 years career. And I learned a lot on concrete, especially for very, very strong concrete.
Engineers add an extra 30 centimeter thick concrete layer at the pier's bases for additional protection. Today, Marcel checks if the team's hard work has been worth it.
These piers were installed at the end of December 2016. That means so far we had 3 winters. So far the behavior is perfect. We're really confident that it will last 125 years for ice abrasion.
Samuel de Champlain Bridge's super strong concrete makes it tough enough to resist destructive ice flows. But new challenges lay ahead. How does this super bridge prevent falling ice that endangers lives? And what technology turns it into an intelligent machine that keeps check on its own health? Workers in Montreal race to complete the city's new super bridge. 37 sets of giant concrete pier legs, 84 meters apart, support most of the bridge's 3.4-kilometer span. A total of 60 cables attached to either side of a 170-meter tall tower hold up a 500-meter section. Only when all the cables have been installed will the bridge be ready to open.
Completing the cables is significant because the bridge at that point will be structurally completed, and the only things that will remain are finishing works.
The pressure is on Jonathan Smart to finish the job.
There's 4 holes, so this is the 4 last cable. After that, the job's gonna be done. Everybody's looking at us and they want their bridge. They want us to finish this bridge. For Montreal, we need this bridge.
Jonathan and his team must install special sleeves that encase the full length of the bridge's 60 cables.
The first step is lifting the sleeve with the tower crane, and we attach this to the anchor up there. When the sleeve is in position, we install cable.
Cable sleeves protect the metal inside from ice and rain. But come winter, some sleeves can create dangers to both traffic and pedestrians. 2014, Charleston, South Carolina. The Ravenel Bridge closes when large chunks of ice fall on passing cars, shattering their windscreens. 9 vehicles sustain damage. It's the way water freezes on the bridge's cable sleeves that's a big factor in creating the falling ice. Temperatures fluctuating just above and just below freezing causes the problem. Rain coats the sleeves in water. When the temperature drops below zero, the water freezes. Temperatures then rise, but not by enough for the ice to melt. New rainwater falls on top of the ice and freezes when the temperature drops below zero again. Soon a thick layer of ice completely encases the sleeve. The ice becomes heavier until it breaks away, crashing onto the bridge deck below. The designers of the new Champlain Bridge must stop its cable sleeves shedding dangerous, large chunks of ice. The ingenious fix is a unique design running the length of the sleeve. A series of equally spaced hoops.
You can see that there are circular ribs. This is a bit different from what you would see on most bridges. The idea here is with these circular ribs will help shed water more efficiently.
The ribs are spaced at 30-centimeter intervals. Because of the cable's slanted angle, when it rains, water accumulates behind the ridges, and most of it runs off and falls onto the bridge deck as harmless drips. The water freezes in chunks trapped between the ribs. The ice sheds in smaller pieces, so when it falls onto the bridge deck, it's not dangerous to passing cars and pedestrians. The sleeves are now in place. Next, Jonathan's team must thread the cable strands.
Outside it's looked like one big cable, but inside there's 127 small cable. You can see here we have a pre-cut cable. That's the cable we're gonna be in this sleeve.
Splitting the cable into so many strands cuts maintenance time and cost. Future maintenance crews will only have to replace damaged individual strands. They will not have to switch out an entire, super heavy cable. Engineers use winches to thread each strand, one by one, up the sleeve and through to cable anchors in the tower. They then pull the ends downwards and secure them to the deck.
These are 5 times the strength of normal steel. These strands themselves are actually doing all the work in terms of supporting the weight of the deck structure.
The next challenge is to tighten the cables to hold the estimated 12,800-ton weight of the bridge's span. What ingenious tool makes sure every cable is stretched to the correct tension? And what technology makes this bridge intelligent enough to know when it needs maintenance? In Montreal, workers race to ready the new Samuel de Champlain Bridge for its grand opening. Once complete, the bridge must support over 1 million vehicle journeys every week and serve the city for 125 years. Advanced super-strong materials and an ingenious design make the bridge windproof, ice-proof, and flexible enough to cope with Montreal's massive temperature variations. But its lifespan depends on identifying and repairing problems before they become critical. Limited access to inspect the structure's interior is a big reason why the old Champlain Bridge is failing. Engineers cannot see critical issues until they show up on the bridge's exterior. By then, it's too late to solve the problem at source. All they can do is patch up the damage. So engineers are building the new bridge to have all area access to avoid these past mistakes. Hatches, walkways, and crawl spaces allow them to inspect every square centimetre of the bridge's 3.4-kilometre span. But they still need help to identify potential problems as early as possible. Borja Baez leads a team tasked with making the bridge intelligent.
We've covered this new Champlain bridge from head to toe with sensors like GPS, corrosion, displacement. This bridge is going to be like one of the smartest structures in the world.
Borja's team installed 226 sensors that send data 24/7 to a central monitoring station.
This is a strain gauge installed in a piece of steel, and just a very small deformation of less than a millimeter, there would be an alert, and the maintenance team would check what's happening in the structure.
The cloak of sensors makes the new bridge hyper-vigilant. Alerting humans to problems early on is a big step towards the bridge achieving its mission of serving Montreal for 125 years. At deck level, engineers race to thread and tension the last remaining cables. They must tighten each of the cable's 127 strands. Mechanics deploy a special tool to tension them one by one.
The gentlemen here are key in stressing the cables to the correct stress level. They put a hydraulic jack which will pull the strand, and then they'll stick these wedges that will lock the strand into place.
Over the next 20 days, the team pulls out all the stops to finish the job. The last cable plugs in right on schedule.
After 1 year and a half, we finally finish the last sleeve. It's an important step of the new Champlain Bridge. The iron workers are very, very proud of this big project. They put a flag, they took photo, they are so proud, and they work so strong to finish this big project. It's a big step for us.
Two months later, at 5 a.m. on the 24th of June, the Samuel de Champlain Bridge opens. The first vehicles roll westwards over the St. Lawrence, on Montreal's newest and toughest crossing. Over 4 years, a 1,600-strong workforce poured 93,000 cubic meters of concrete, laid over 72,000 tons of steel, tightened 1.2 million bolts to span the mighty St. Lawrence River. Its mission accomplished for Guy and his team.
To work on the project of this magnitude is almost a dream, because you don't build these sort of bridges very often. And I think every single person that has worked on this bridge is proud of having contributed, because it is a landmark structure in Montreal, and it's going to be there for many generations to come.
The Samuel de Champlain Bridge is tougher and will carry more vehicles than any other bridge in Canada. Built into its mighty frame are 5 engineering marvels that make it the pinnacle of bridge design. Ribbed cable sleeves stop dangerous ice falling onto passing cars. A vented design keeps the deck steady in the strongest winds. Expanding joints allow the bridge to flex when the temperature changes. Pier legs built from super strong concrete withstand the force of crushing ice. Innovative drainage gets rid of corrosive salty slush. This is a bridge that is big, tough enough to survive anything Mother Nature throws its way, and is set to become a Montreal icon. The Samuel de Champlain Bridge is built to be the ultimate. At 315 meters long and 65 meters tall, this is one of the largest cruise ships on the planet, MSC Bellissima. This Leviathan carries over 5,500 guests to destinations all across Europe.
It's a self-sufficient city which has to be comfortable for the passengers.
How did engineers build a cruise ship this big? And what innovations keep it sailing all year round?
Cruise ships today are absolutely engineering marvels.
We unlock the secrets that help this vessel deliver a super smooth ride. From ingenious stabilizers that keep the ship level in the roughest seas, to near-silent propellers that thrust it fast through the water, to reveal what it takes to build the ultimate mega cruise ship. The Mediterranean coast. Tourists flock to these spectacular shores to soak up the area's rich history, culture, and sunshine. Over 3 million of them each year choose to take it all in from the comfort of a luxury mega cruise ship. 12 cruise operators, running a total of 40 supersized vessels, compete for a slice of the $60 billion Mediterranean holiday market. Success must be hard won. Passengers demand 5-star service, spacious outdoor areas and big pools, and a varied itinerary stopping off at spectacular locations for a once-in-a-lifetime experience. To corner the market, operator MSC Cruises built this extraordinary cruise ship. It's called MSC Bellissima. 315 meters long, 43 meters wide, and 19 decks high. This is MSC's biggest ship, designed to operate year-round across the globe. Bellissima is built using innovative engineering hidden inside its mighty frame to help give passengers the ultimate cruise experience. A unique hull design allows it to glide into shallow European ports. Superfine membranes filter molecule-sized particles to turn salty sea into pure drinking water. An ingenious scrubber system cleans noxious chemicals from exhaust released above the deck. All these elements combine to make MSC Bellissima the ultimate cruise ship. 11 a.m., Barcelona, Spain. Bellissima opens its gangways to receive passengers. Immigration purser Alfonso Gargiulo has just 6 hours to get all of them aboard.
MSC Bellissima is almost fully booked. We have on board about 5,600 guests. This is the most critical moment for us.
Across the ship, the 1,500-strong crew complete final preparations before the vessel leaves port. Ahead lies a 7-night voyage, stopping at 6 iconic Mediterranean cities. From the port of Barcelona, Bellissima heads northeast along the Spanish and French coasts. First stop, Marseille. The voyage continues into Italian waters. Next stop, Genoa, to take on board vital supplies. From here, the ship heads southeast, stopping at Naples and Messina. The ship then calls into Valletta, Malta, before it makes the 1,200-kilometer trip back to Barcelona. Bellissima owes its origins to the classic liners of the early 20th century. These ships transported passengers across the Atlantic Ocean. They were the biggest vessels of their day. Their V-shaped hulls were designed to carve through oceans in all sea states. Bellissima is double the size of a traditional liner and carries triple the number of passengers. Building a ship this big, with a draft shallow enough to enter the most popular Mediterranean ports, is a huge engineering challenge. A ship's draft is the distance between the bottom of its keel and the waterline. The more load a ship carries, the deeper its draft becomes. A large traditional liner carries 2,000 passengers over 12 decks. The ship's 8.5-meter draft is shallow enough to enter most harbors. Today's mega cruise ships need extra decks to entertain thousands more passengers than the largest classic liners. Simply adding this extra weight to a standard liner design would make its draft so deep that the ship could run aground in port. Solving this problem fell to shipbuilders Chantier de l'Atlantique when they designed and built Bellissima back in 2016. The engineers at this facility in France weld over 1,000 tons of steel every week to construct MSC's fleet of mega cruise ships. Design manager Guillaume Lagree must balance every new vessel's size with its need for a shallow draft.
The first discussion we have when we design such a ship is to define the ports where the ship will go, and this will give us the main dimension of the ship. When you look at all the Mediterranean ports, the limit is about 330 meters for the length, and for the draft, 8.5 meters enables to go everywhere.
Guillaume sculpted Bellissima's hull to make the supersized cruise ship float higher in the water. A ship floats higher and reduces its draft when it spreads its weight over a larger area. Guillaume's team takes a traditional hull shape and stretches it longer and pulls the beam wider to 43 meters, increasing the area of its hull in contact with water compared to older designs. The team also flattens the keel for extra clearance over marine obstacles. On paper, this ingenious design means Bellissima can carry its 7,000 passengers and crew high above the waterline. The mighty cruise ship should glide into most ports with no danger of running aground. Bellissima's innovative design is just one part of the solution. Classic liners were constructed from thick steel plates riveted together. This made them strong, but also very heavy. Building Bellissima's huge structure using these traditional techniques and materials will cancel out the benefits of the ship's hull redesign. Any vessel still risks grounding if it weighs too much. At the shipyard, engineers use an innovative construction method to keep the frames of ships like Bellissima as light as possible. They build ships by welding together boxes made from weight-saving sheet steel. Project manager Elise Guérin oversees the operation.
For a steel engineer, it's quite a challenge. There are more than 300,000 parts which have to be welded together to form the ship.
Construction work began on Bellissima in November 2016. First, robots welded together 3-meter by 20-meter steel sheets to make Bellissima's deck. They're less than 10 millimeters thick to save weight. Workers welded on lengths of metal called stiffeners to strengthen the decks. Next, computer-controlled plasma cutting machines sliced more steel to make the deck's walls.
It cuts up to 22 kilometers of steel every week. It is a very powerful cutting machine, which never stops.
A team of welders joined these wall pieces to the decks to make a giant reinforced hull section. Next, they joined together an average of 12 hull sections to build a mega block. This is a super huge ship section, 43 meters wide and 10 meters tall, weighing more than 1,000 tons. Elise's team used one of the most powerful gantry cranes in Europe to lift and place each of the 50 mega blocks that make up Bellissima. The crane operators had to align each block with millimeter precision.
Fitting a block is a big challenge. You've got a very small tolerance in order to be able to adjust the block to the ship. Every day we fit a new block. It's amazing.
It took Elise's team around 18 months to turn 35,000 tons of steel into the finished Bellissima. Mega blocks make it possible for engineers to build a vessel that weighs almost the same as a traditional liner, but is double the size. Constructing Bellissima from thin but tough steel keeps the ship's 7,000 passengers and crew high in the water and eliminates the possibility the ship will run aground in port. In Barcelona, immigration purser Alfonso checks in the last passengers.
I just informed the bridge, we are ready. A bit late, but all on.
The dockside crew releases Bellissima's mooring lines. The ship's huge engines thrust it out of Barcelona. The 8-day voyage begins. What ingenious technology makes the propellers on this mighty ship near silent? And how does it create 12 million liters of drinking water out of the salty sea? Cruise ship MSC Bellissima powers across the Mediterranean Sea towards the city of Marseille on the French coast. It's 10 p.m. on the first night of the ship's 8-day cruise. Most of the 5,600 passengers on board enjoy the evening in one of the ship's 32 bars and restaurants. Over 1,000 descend on the vessel's 2 theaters to watch live performances. At the end of the night, passengers retire to their cabins Each one of them expects to wake up refreshed for their second day of cruising. Housekeeping manager Supriyanto must ensure every passenger on board gets a good night's sleep.
When they go to bed, they don't want to listen to any noise. And when the ship is quiet, less vibration and everything, of course, satisfaction more.
The ship must travel overnight at a speed of up to 20 knots or 37 kilometers per hour to reach Marseille by 8 a.m. Below deck, 4 huge diesel-electric engines together produce 40 megawatts to power the vessel's pair of 6-meter diameter propellers. Insulation stops engine noise from disturbing the passengers sleeping up above. But this insulation does very little to quieten the noise made by the spinning propellers. The faster a propeller rotates, the more thrust it produces. An area of low pressure forms in front of each propeller blade as it slices through the water. The pressure is so low, the water boils. This creates thousands of tiny steam-filled bubbles on the surface of the blades. These bubbles pop. This phenomenon is called cavitation. One tiny bubble pop on its own doesn't matter. But thousands, all popping simultaneously, can send powerful, noisy vibrations pulsing through the entire ship. Bellissima must eliminate disturbing cavitation noise to guarantee the ship's passengers get a good night's sleep. It fell on the shoulders of hydrodynamic engineer Loïc Moron to solve this problem.
Cavitation is like a hammer which impacts a steel plate. It's very, very noisy and it's very disturbing. So we have to avoid these situations on the cruise ship, that's for sure.
Many traditional propellers have 3 blades. Their fast rotation generates huge thrust to push a ship forwards. But the propeller's fast turning speed creates noisy cavitation. One solution is to slow the propeller's rotation. This will generate fewer bubbles and cut cavitation noise. But slow propellers will reduce a ship's thrust. To bring the ship back up to speed, Loïc's team adds 2 extra blades to each of the ship's 2 propellers. 5 blades increases the propeller's surface area, pushing against the water. This boosts thrust for little increase in cavitation. These special propellers allow the ship's passengers and crew to enjoy both a fast and quiet ride. In this giant foundry, engineers forge propeller blades from an aluminium-bronze alloy. This alloy is over 90 times more resistant to corrosion than steel. Robots cut and polish the cooled metal according to a precise computer design to shape the 5 blades.
We usually make each blade in an independent way because the blade's geometry is very complex, which makes the manufacture also complex.
The individual blades slot into a central hub to create a giant 6-meter diameter propeller, weighing over 30 tons. Bellissima's 2 propellers attach to a pair of mounts fixed to the ship's stern. In 2018, technicians used electronic meters to measure the cavitation noise made by Bellissima's propellers. They concluded the ship's propellers are amongst the quietest installed on any operational cruise ship.
We are very happy with the final results. We have reached a very good high-level performance.
In the Mediterranean, the ship sails serenely towards Marseille. The guests on board sleep peacefully.
During early morning, as you can see that the corridor is very quiet and don't hear any noise. All our guests are sleeping well, so I'm so happy with this one.
"8 a.m. Bellissima pulls into Marseille right on schedule. The passengers disembark. They enjoy all the sights and sounds of the famous French city before returning to the vessel 8 hours later. At 6 p.m., the ship sets sail once more. Destination, Genoa in Italy. Ahead lies a huge challenge for the ship's crew. They must keep over 5,600 passengers fed, whilst navigating the vessel for over 2,000 kilometers through turbulent seas. What engineering secret helps this mega ship stay stable in the roughest waters? And what technology allows it to produce fresh water on demand?
Perfect.
8 a.m. Day 3 of MSC Bellissima's 8-day voyage around the Mediterranean. The mighty cruise ship docks at the Italian port city of Genoa. Here, the crew loads 381 tons of provisions into the ship's 21 giant storerooms below deck. The supplies include 8 tons of flour, 14 tons of meat, and over 20 tons of fresh fruit. Bellissima now carries enough food to keep all passengers and crew fed for the remainder of the voyage. But this ship's lifeblood is fresh water. Servicing the needs of just one of the 7,000 passengers and crew on board consumes around 200 liters of water a day. The supersized ship's mega laundry room alone uses tens of thousands of liters of water to wash up to 13 tons of linen every 24 hours. This water must be clean and salt-free to keep the vessel running smoothly.
If we have, let's say, bad quality of water, of course it will affect in all the linens and towels. It will impact in really big hotel operation because it doesn't have linen for the restaurant, doesn't have towels for the pool, we stop.
Together, the ship's passengers, crew, and all its processes consume 12 million liters of water during a typical 8-day voyage. That's enough to fill nearly 5 Olympic-sized swimming pools. Supplying this amount of fresh water is a huge engineering challenge. Room on board the ship is at a premium. Cabins and entertainment areas take up 74% of the space on board. The engineering department and guest services, such as the laundry, occupy a further 23%. And the vessel's fuel, ballast, and waste tanks another 2%. That leaves enough space to carry just 5 million liters of water. Less than half of the 12 million liters Bellissima needs to run systems and supply its 7,000 passengers and crew for their 8-day voyage. At this shipyard, engineers deploy an innovative technology to make sure Bellissima and its sister ships never run out of fresh water. Project manager Antoine Gondet oversees the operation.
If you don't have enough fresh water on board, then it can very, very quickly turn into a drama and you are forced to stop the cruise.
Hidden deep inside Bellissima is an ingenious system that turns over 1 million liters of seawater into fresh water each day. Pumps suck seawater into the ship through pipes in its hull. Layers of sand and special carbon filter out the largest pieces of debris. Next, filters remove microscopic contaminants 50 times smaller than a human hair. Then the water passes through columns, each containing a spiral of molecular membranes. The superfine membrane weave separates salt chloride ions from water molecules. Once free of salt, this fresh water is ready to use on board. The process converts almost 10 liters of water per second when the ship is at sea.
Because the cruise ship is spending half its time at sea, these plants have a huge production capacity to fulfill the needs of the vessel within half a day.
At the end of day 3 of the cruise, the mega ship departs Genoa and heads out into open sea. It's now the water plant below deck kicks into action. Powerful pumps pressurize the fresh water. They push the liquid through dozens of kilometers of plumbing woven throughout the ship. Vice President of Environmental Operations and Compliance, Minas Miatidis, must ensure the system works without a hitch.
Our production capability is over 3,000 cubic meters per day and distributed to over 2,000 cabins, the galleys, the laundry, and all other technical areas that we need to use fresh water.
20 giant tanks each hold up to 250,000 liters of desalinated water. This liquid must pass through one last process before it's fit for passengers to drink.
The final part is where we add the chlorination and where we manipulate the pH level of the water so we have absolutely crystal clear, perfectly tasty, good fresh water. Look at that.
Yeah.
Nice MSC Bellissima produced water. Salud. Perfect. Very good.
It's the morning of day 4 of Bellissima's cruise. The mega ship docks at Naples. Passengers disembark to visit the famous Roman ruins of Pompeii. They return to the vessel 6 hours later. The mega ship leaves port en route to Messina on the island of Sicily. But new challenges lie ahead. Strong Sirocco winds can make this part of the journey very bumpy for the passengers and crew. What ingenious technology keeps this mega ship stable in the roughest seas? And what is its secret for producing some of the cleanest emissions of any ship in its class? In the Mediterranean, MSC Bellissima powers across open water between Naples and the Sicilian city of Messina. It's dinner time on day 4 of the vessel's 8-day cruise. Thousands of passengers enjoy meals in one of the ship's 4 huge restaurants. Maitre d' Vincenzo Porzio must make sure every diner receives 5-star service.
The peak hour is start from 8:30 until 11 o'clock. We serve already, I think, 10,000 meals.
But feeding thousands of people every mealtime at sea is a big challenge. Sudden changes in weather can make this stretch of water rough and cause the ship to pitch and roll. Choppy seas make any ship move from side to side, risking spills and even injuries on the restaurant floor.
It's not easy to work with the rolling of the ship.
And if the ship encounters a big squall, the effects on board can be devastating. This dramatic footage shows cruise ship MV Astoria caught in stormy seas off the coast of the United Kingdom. Many passengers on board suffer nausea. one person is airlifted to hospital. The higher a ship floats in the water, the greater the effect can be of violent movements caused by rough seas. Bellissima's towering 65-meter height makes it vulnerable to a phenomenon called parametric rolling. Large, regularly timed waves hitting the ship head-on make the vessel seesaw. When a large wave reaches the back of the vessel, it makes the ship tip forwards. The way the weight is distributed across a ship this tall can then cause the vessel to roll to one side. When the next wave hits, it rolls back the other way. Each new movement is more extreme than the last. The rolling increases the chance of passengers suffering seasickness and ruining their holiday. At the shipyard where Bellissima was constructed, engineers worked to solve the problem. First, they identified the specific type of ship movement that causes passenger sickness.
We are more sensitive to the rolling motions than pitching motions. As soon as you have a very big ship is reacting faster to the waves. So in a sense, you will get higher accelerations, more like pong pong. Higher the accelerations you get, and a better chance you get to be seasick.
To minimize this rolling motion, engineers installed a pair of these fin-shaped stabilizers into the vessel's hull.
We need to have the most comfortable ship for the guests, so that's the reason why we need the stabilizers.
The stabilizers arrived at the shipyard as a pair of complete units, ready to plug into holes cut into the ship's hull. Hydraulic pistons move their articulated wing-shaped fins, measuring 5.6 meters long by 2.5 meters wide. These stabilizers are Bellissima's secret to smooth sailing in all weathers. Sensors on each stabilizer measure the direction and degree of the ship's roll. If the motion goes past just 1 degree, Bellissima's crew can deploy the pair of stabilizer fins stowed inside its hull. The fins work like wings to correct the ship's roll. If the sensors detect the ship rolling starboard, they automatically instruct the fins to rotate, shifting the vessel the other way. In big seas, the system works continuously to level out the rolling motion, ensuring Bellissima's passengers and crew experience a smooth ride. Up on the ship's bridge, officers monitor the weather. They take no chances on this stretch of water. They give the order to activate the stabilizers. It's the responsibility of Chief Engineer Luigi De Martino to make sure they deploy without a hitch. A pair of 1.6 meter long pistons turns bearings that swing each fin into position. A computer automatically adjusts the angle of the fins to counteract any roll caused by waves buffeting the ship.
In the bad weather condition, they're moving up to 16 degrees. 16 is the maximum angle allowed for a fin stabilizer.
Each fin is just 13% the width of Bellissima's hull, but their combined effect on the ship is huge.
This system can reduce up to 90% of the rolling motion of the ship. If the ship rolling 10 degrees, our stabilizer unit can be reduced to 1 degree. Now it's really impressive. The passengers are very glad to be on this ship because it's comfortable for everyone.
The vessel stays rock steady with the stabilizers deployed. They make it possible for Vincenzo's team to wait on every table without danger of being thrown off balance.
It's fantastic. It's amazing ship. We have the top technology of the world.
The vessel arrives at Messina on the morning of day 5 of the cruise. After a 10-hour stay in Sicily, it will power onwards to Malta, and this mega ship will face new engineering challenges. What innovative technology keeps the air around the outside decks free from noxious exhaust gases? And what's the secret to maneuvering this Leviathan into the tightest ports? 8 a.m., day 6 of MSC Bellissima's 8-day tour of the Mediterranean. The mighty cruise ship docks at Valletta, the capital of the island of Malta. Passengers disembark to explore the winding streets of the old city. On the ship, some guests relax on the sun deck, whilst others take the plunge in the vessel's water park. It's the job of pool supervisor, Alonso Stewart, to ensure nothing spoils the guests' outdoor fun.
Here we can have 600, maybe 700 passengers per day going around at the aqua park. It's a lot of people to keep happy, but the passengers come here to take fresh air. That's the important part.
Guaranteeing good air quality across a cruise ship's outside spaces is a tough challenge. The ship needs a reliable source of power to run all its essential systems and provide all services and passengers on board with a constant stream of electricity, even when the ship is docked. Bellissima's 4 diesel-electric motors work around the clock. At peak output, they produce 67 megawatts of electricity, enough to power 50,000 homes. Burning heavy fuel oil produces exhaust gases. Many cruise ships vent these fumes from funnels positioned above the top deck. These outlets on Bellissima are just a few meters above the ship's popular aquapark. Making sure passengers don't breathe harmful gases is a big engineering challenge. Classic liners solve the problem with long exhaust funnels. These release dirty, sulfurous fumes high above the top deck. Bellissima's uppermost public space is over 55 meters high, nearly twice that of a classic liner. And it's around 10 meters from the ship's exhaust outlet. Simply making Bellissima's funnels longer will create a big problem when the megaship enters ports spanned by low bridge decks. At this shipyard in France, workers race to finish building Bellissima's sister ship, MSC Virtuosa. A giant equipment install reveals both ships' secret to beating harmful fumes. A pair of huge steel drums, 5 meters in diameter and over 10 meters tall, each weighing 20 tons. They're called scrubbers. They remove almost all of the environmentally damaging sulfur compounds from the engine's waste gases as they move through the exhaust system.
The sulfur is really dangerous for health, but such machine like scrubber is able to very efficiently remove it, so we don't have to breathe it. So the scrubber will be in use every day.
Nozzles inside a scrubber's drum spray over 22,000 liters of seawater per minute into beds packed with metal filings. Engine exhaust gases rise through the moist beds. Pollutants dissolve into the water. Water droplets trickle down the inside of the drum and collect in a treatment chamber. Here, a chemical process separates the clean water from pollutant. The waste forms a sludge, Experts responsibly dispose of this waste on land when the ship is in port.
The scrubber is using seawater to rinse the exhaust gas. You can imagine being inside the scrubber. You can call it a crazy shower.
In the Mediterranean, Bellissima departs Valletta and powers forwards into open water. The ship's captain sets a course for its final stop, Barcelona. The scrubbers kick into high gear to clean waste gases ejected by the ship's 4 giant diesel-electric motors.
The system has the ability to remove 97% of the sulfur dioxide that is contained into the exhaust gas. And that sulfur, it never goes on the air, never goes in the sea, and then it is removed when we are in port. If you go out and if you sit on the open decks, you're going to see the big difference that the exhaust gas cleaning system has for everybody.
On the top deck, guests are busy racing down the water slides or working on their tans, oblivious to the ingenious technology working in the background.
We start this morning full from the first moment until the end. Today, the here is very nice. The passenger enjoy the slides 100%.
1,200 kilometers of open sea lie between the vessel and Barcelona. Will this giant ship arrive on schedule? And what is its secret for docking in the narrowest, busiest ports? In the Mediterranean, cruise ship MSC Bellissima closes in on Barcelona. The port city is the last stop on the mighty vessel's 8-day, 3,000-kilometer journey. It's the job of Captain Raffaele Pontecorvo to dock Bellissima inside the busy harbor. He and his officers must reverse the vessel 2 kilometers down this narrow channel to reach it. Parking backwards means the ship will be facing the right way for a fast departure later this afternoon. But guiding this ship to its berth is a huge challenge. The vessel's tall profile makes it vulnerable to high winds blowing it off course. One wrong move during the reversing maneuver and it could collide with another mega ship.
We have always to take care about the wind. It's really a big responsibility, taking in mind that you are the only responsible for the life of more than 7,000 people.
Bellissima relies on a responsive steering system to help guide it through narrow channels in all weather conditions. At the shipyard in France where the vessel was built, engineers prepare to install a sister ship's propulsion system. A pair of 20 megawatt electric motors in waterproof housings called podded thrusters. They work differently from fixed propeller propulsion systems. The pods swivel their propellers to direct thrust precisely where it's needed.
For this very big cruise ship, we prefer to use the pod. So all this unit can move 360 degrees, so that makes the maneuvering much easier, much faster, and which allows to the captain to be able to park the ship into the very complex harbor.
Bellissima carries a pair of podded thrusters at the rear. 4 fixed thrusters in the bow direct powerful jets of high-velocity water to help steer the ship from the front. Together, they make Bellissima highly nimble for such a huge vessel. Outside Barcelona port, Captain Raffaele engages the podded thrusters. They slowly turn the vessel through 180 degrees. ship is ready to begin its 2-kilometer journey to its berth. The wind today is a favorable 8 kilometers per hour. But threading this giant ship through the port's entry channel is still no simple task. Moored up on one side is a mega cruise ship. On the other, a massive container vessel. It's the job of Environmental Engineering Officer Pasquale Maresca to help steer a perfect line between them.
We have a ship on port and starboard side, and we take care of the distance from port and starboard, because we have around 50 meters one side and 30-40 meters another side.
Pasquale relays readings from this laser measurer to track the distance between Bellissima and the moored megaships.
Distance from the bow to the aft.
Yes, at the moment 100.
Okay, we push a little bit more the bow to port.
Bellissima's berth comes into view.
Forward 40 meters.
Captain Raffaele turns the rear thrusters and pulses the bow thrusters to delicately maneuver the 315-meter-long ship alongside the quay.
Okay, okay.
Okay, we are in position, we proceed alongside. Okay, finish with the engine. Okay, thank you, staff.
The mega ship completes its 8-day, 3,000-kilometer voyage right on schedule.
The weather was nice. There was not more than 4 knots wind. Good visibility. It was really good. It was fantastic.
Passengers disembark to return home after their Mediterranean adventure.
It's nice for the guests. They are very happy on board, and they are upset when they are leaving it. So it means they really enjoy the vessel.
MSC Bellissima is one of the most innovative mega cruise ships in the world. Built into its mighty structure is a series of engineering marvels that make this ship the pinnacle of passenger vessel design. A wide hull and small draft allows it to slide into the shallowest ports. Extra quiet propellers drive the ship without disturbing the guests. An ingenious water plant turns salty sea into crystal clear drinking water. Fin stabilizers keep the ship steady in the roughest weather. Exhaust scrubbers clean waste gases and reduce noxious emissions. This giant passenger vessel is one of the world's biggest cruise ships. MSC Bellissima is built to be the ultimate. Racing across Italy at 300 kilometers per hour. A $38 million super machine. The Italians call it the Ferrari train.
It's a very big challenge running at this speed. Everything must have to be designed properly.
The AGV is one of the world's fastest passenger services. What makes it so quick? And what stops it from hurtling off the track as it speeds passengers from Milan to Rome?
I'm traveling at 300 kilometers per hour. It's quite impressive.
we unlock the engineering secrets that help this high-speed train reach its destination on time. From the intelligent rooftop power supply that feeds this beast with 25,000 volts of electricity, to the innovative electric motors that thrust it up the steepest inclines, to reveal what it takes to build the ultimate super train. Italy, a nation of 60 million people, all in a rush to get somewhere. Few places are busier than the city of Milan, Italy's premier business hub. More than 320,000 people a day travel through Milan's central station. They need fast, reliable links to industrial cities in the north, and Rome, Italy's capital, to the south. This is the machine they rely on to keep their day on track. The AGV. Its operational speed is capped at 300 kilometers per hour. But its max speed of 360 kilometers per hour makes it the fastest passenger train in Europe. Each one costs $38 million to build. The company that runs the train, Italo, operates a fleet that services 25 Italian cities. It runs an average of 54 services between Milan and Rome each day. A high-tech control center guides these advanced trains along the tracks, while engineers work 24/7 to keep them maintained. Italo's aim is to shuttle passengers to their destination as quickly as possible. To achieve this, the AGV train is built with innovative technology hidden under the hood to help speed it between cities. Electric motors with more power than a Formula One race car drive the train up inclines at full speed. A network of intelligent cables channel 25,000 volts into the AGV's power system. Ingenious friction-boosting technology helps the train maintain its grip on the wet and greasy tracks. All these elements combine to make the AGV the ultimate high-speed train. Today, the man at the controls of this super train is driver Dennis Laraya. The time is 7:53 a.m. Dennis has 35 minutes to complete his pre-flight checks.
Adesso sto facendo la prova del freno. Adesso questa è l'area nella condotta generale. Si è intercettato, bisogna aspettare 1 minuto per vedere che non perde, che non vada giù.
His mission today is to safely transport 460 passengers, 567 kilometers, from Milan to Rome in 3 hours and 30 minutes.
Avere tante persone sopra è comunque una responsabilità. È una bella motivazione per me.
Failure means more than dented pride. Retaining the company's place in Italy's transport market relies on delivering a first-class service. Breakdowns, late arrivals, an uncomfortable ride all risk damaging the operator's reputation with passengers. It's critical Dennis gets his train to Rome on time. But his machine must cover nearly 600 kilometers of challenging track to reach its destination. Dennis must guide the train along a high-speed line through the suburbs of Milan and across northern Italy, before stopping at Reggio Emilia and Bologna. The route crosses the Apennines and speeds through tunnels, stopping in Florence, before negotiating the web of suburban train lines that lie north of Rome, to reach Rome Central Station 3 hours, 30 minutes after leaving Milan. (8:09 a.m.) Hundreds of passengers on Milan Central's busy concourse file onto platform 6 and board Dennis's train. The interior is designed to make their 3.5-hour journey as comfortable as possible. All 462 seats on board are made from leather. Each of the carriage's windows are 15% larger than on standard commuter services. Shock absorbers between the wheels and carriages reduce vibration. And the Italo looks fast. Owing to its red livery, the AGV is dubbed the Ferrari train. 8:12 a.m. Some 600 kilometers south in Rome, Italo's control room tracks the position of every AGV. Operations Director Sofia Appadula must ensure every train is ready for dispatch.
99:15 macchina.
Siete pronti per la partenza?
Siamo pronti.
Mi confermate il binario numero 6? Sì? A tra poco, grazie.
Ok, a dopo, ciao.
In Milan, the train manager closes the doors. Dennis receives the all clear to proceed.
We're ready.
The train departs on time at 8:35 a.m. As the onboard crew serve passengers breakfast, Dennis turns up power on the train's 10 electric motors. This is a machine that is built to go fast. With a top operational speed of 300 kilometers an hour, it's one of Europe's quickest passenger trains. And everybody on board expects it to live up to that promise.
Being on time, it's fundamental in my work because we have several meetings to attend like every day. So being late at just one of them means being late at every single meeting after it.
The first challenge for Dennis is to keep the train running fast along all sections of the route to Rome. This will be no simple task. Long sections of track climb hills. These inclines can slow down traditional trains. Many older passenger trains are pulled by a single locomotive at the front, or pushed and pulled at the same time, with a second locomotive adding power from the rear. This standard configuration is fast on the flat, but can rapidly lose speed up hills. When climbing inclines, carriages in the middle lose forward momentum and pull back on the locomotive. This slows the train. When the locomotives increase their power and accelerate, the lagging carriages are brought back up to speed. But the train loses valuable time. The engineers who built this super train designed an ingenious solution to help power this machine up inclines. This depot in southern Italy is where workers maintain Italo's 25-strong fleet of AGVs. Here they strip off a train's red coat to run regular checks under the hood. Francesco Vidanza leads the team responsible for keeping every Italo train running. A critical inspection of the AGV's sets of wheels, called bogies, reveals the machine's secret for staying fast.
This is a powerful motor bogie from the AGV. You can see the two big motors. They are permanent magnet motor, very powerful, but very little.
Engineers drop the traditional two-locomotive design and decide to turn carriages into locomotives to maintain this machine's momentum up inclines. They fit a pair of innovative motors to 5 of the train's bogies. Each motor has more horsepower than a Formula One race car. The system is called distributed power. Distributed power spreads out the AGV's thrust along the length of the train. This allows the train to maintain a constant speed, as none of its carriages will lose momentum and drag the AGV back when going uphill. Each of the bogies' motors drive a pair of the train's wheels. More wheels under power means motorized carriages pull their own weight, boosting the train up inclines with no drop in speed. So the AGV stays fast along high-speed sections of track. Train driver Dennis puts the pedal to the metal. He accelerates train and passengers up to the top speed of 300 kilometers per hour.
Being this fast and sitting on a chair and then traveling at 300 kilometers per hour, it's quite impressive.
30 kilometers into the journey, the train is right on schedule.
Treno sta viaggiando in orario, non ha problemi, quindi sta andando tutto regolarmente.
To reach Rome on time, Dennis must keep the 423-ton train close to full speed. But this is a challenge. What technology keeps the AGV fed with 25,000 volts of electricity? And what is this train's secret for staying on the rails? In northern Italy, the Italo AGV high-speed train is nearly a quarter of the way into its 600-kilometer journey from Milan to Rome. The 460 passengers on board need to arrive in Italy's capital on time. The machine's reputation rests on the train reaching its destination in 3 hours 30 minutes. 150 kilometers into the journey, driver Dennis must make a stop at Reggio Emilia. It's the job of train manager Angelo Pansera to get 70 new passengers on board within 2 minutes. But there's a problem.
Indications in the platform are not correct.
The station's monitors are displaying the carriage's numbers the wrong way round.
Because we have coach number 11 that way and not coach number 1 as it is written on the monitors.
Confused passengers struggle to find their seats. The clock is ticking.
They have to correct now to help the passengers to their correct coach. He's ready, we can go.
With the passengers finally boarded, Dennis powers his super train towards Rome.
Grazie. E buongiorno. Grazie.
But the delay has pushed it 2 minutes behind schedule. For Dennis's AGV to pick up the pace and reach Rome on time, the train must be fed with a reliable supply of electric power. The AGV is just one in a long line of pioneering trains using revolutionary power systems to push the limits of speed even faster. Back in the late 1930s, trains powered by steam first break the 200 kilometers per hour barrier. Almost 4 decades later, diesel trains, like Britain's Intercity 125, hit over 240 kilometers per hour. In 1981, The electric TGV achieves speeds in excess of 300 kilometers per hour on a new high-speed track. Electric trains win out against diesel and steam in the speed stakes because they're lighter. Their engines take up less space and they carry no fuel on board. The AGV's lifeblood is 25,000 volts of electricity. It passes through overhead cables that are strung above the track. The electricity powers the train's 10 motors and all essential onboard systems. Electricity flows from the cables to the train through steel arms called pantographs. Keeping the pantograph in contact with the cable whilst traveling at 300 kilometers per hour is a huge engineering challenge. The connection between the cables and pantographs must be perfect. Small bumps in the track and tiny changes in the height of the cable could vary the distance between the train and its power source. If the pantograph presses too hard or is misaligned with the cables, it could damage valuable infrastructure or destroy the pantograph itself. If the pantograph loses contact, electricity could arc across the gap between the conductor and the cable. This could potentially trigger a fire and endanger the crew and passengers. This footage from another train shows what can happen when a pantograph malfunctions. The steel arm disintegrates and brings down overhead cables, resulting in costly damage to critical infrastructure. Sometimes bad weather, such as ice, prevents a perfect connection and electricity arcs between pantograph and cable. In extreme circumstances, electrical arcing can be dangerous. This footage shows how it can set train carriages on fire. To make sure the pantographs on Dennis's train keep in perfect contact, the AGV's engineers build a simple but ingenious solution into this machine. The key to the pantograph maintaining exactly the right contact with the overhead wires is hidden inside its base. A pneumatic cylinder moves the pantograph's steel arm up and down. The system is controlled by a computer. It intelligently adjusts the pantograph's position relative to the cable. To ensure the articulated arm doesn't crash into or pull away from the train's source of electricity. The pantograph's pneumatic cylinders guarantee Dennis's train has a safe and constant power supply. But they can't prevent everyday wear and tear. Friction with the overhead cable degrades the pantograph over time. This can increase the danger of mechanical breakdown and destroy any chance of Dennis's train reaching Rome on time. Italo's fleet of machines undergo regular checks here at this maintenance depot in southern Italy to ensure all the train's pantographs are in full working order. Engineer Francesco Fidanza must protect his team from being fried by 25,000 volts of electricity as they gear up for today's inspection.
Francesco is applying the lockers on this box that contains the key to power on the train. So no one can take the key while the locker is installed. This is a safety rule that we have to strictly follow in order to be safe on train.
With the train locked down, the maintenance crew get busy. This 145-centimeter long strip of graphite fixed to the leading edge of the pantograph is the train's secret to beating damage caused by friction. Graphite is heat resistant and conducts electricity. The strip wears away, protecting both the overhead cables and the pantograph's metal frame from damage. Every 7,500 kilometers, engineers check the graphite strips are thick enough to be safe. If they're too thin, there's the possibility they could damage power lines and start a fire.
By measuring the thickness, we are able to foresee if the pantograph is good or not to continue the commercial service. Here we have 25, so at least we are okay for 30,000 miles.
The maintenance crew grinds down the strip's rough edges to improve contact with the cables before the train leaves the depot to re-enter service. It's the graphite strips built into the AGV that means Dennis can draw down 7,500 kilowatts of electricity into his train's 10 motors and power his passengers towards Rome at 300 kilometers per hour. Up ahead, a new challenge awaits Dennis's train. The Apennine Mountains. Here, the track bends around tight corners. The terrain is uneven, and passing over numerous bridges and viaducts could make the journey very bumpy. How does this super train beat topography and uneven track to guarantee a smooth ride? And what's its engineering secret for staying on the rails when traveling at full speed? In Italy, the AGV train is 200 kilometers into its 600-kilometer journey from Milan to Rome. The passengers on board expect to reach their destination on time. The AGV's operator, Italo, aims to shuttle trains between cities as quickly as possible. To deliver on that, this machine is built for one thing: speed. Paolo Belforte was part of the team that designed Europe's fastest passenger train.
Very big challenge running at this speed. Everything has to be designed properly.
The ultimate fast passenger train was born in one of the world's most advanced train construction companies. French manufacturer Alstom built state-of-the-art locomotives and carriages at 30 production sites worldwide. To make their trains shells, robots cut 3,800 square meters of paneling from sheets of super-thin aluminium. The metal's light weight makes the trains fast. The wheels for the carriages are made from specially hardened steel, tough enough to withstand spinning at 1,800 RPM for hours at a time. A team of 450 workers then assemble the thousands of components needed to make each train. 3 kilometers of pipes and ducts, 300 kilometers of electric cables, 690 kilos of paint.
I'm very proud of being traveling on this train. When you start from scratch, you always see drawing and you can imagine what it will be, but you never know. And seeing this machine working properly with the right comfort and full of passenger is a very big satisfaction at the end.
220 kilometers from Rome, Dennis's train is running 2 minutes behind schedule. The journey up ahead is far from straightforward. The track through the Apennine foothills twists and turns around the hilly terrain. It's critical the train stays on the rails around every bend. Leaving the track at high speed could have devastating consequences. The 24th of July, 2013. This Alvia train enters a tight bend at more than twice the 80 km/h speed limit. The derailment near Santiago de Compostela, Spain, reportedly kills 80 people and injures 144. Investigators conclude the train's high speed caused the crash. To prevent disasters like this happening to Italo's AGV, engineers fit the train with an auto speed limiter. If a driver attempts to go over the limit, the train takes over and applies the brakes automatically to slow the machine down to the correct speed. Secure on the rails, the AGV journeys safely towards the Apennines. Denis's train must cross the numerous bridges and viaducts that span the mountainous terrain here. For passengers traveling aboard a high-speed train, these structures have the potential to transform their journey into a roller coaster ride. All cross-country trains travel on rails laid onto sleepers. These sleepers are often embedded in a layer of rough stones that run on top of an earth embankment. Over time, small movements in the soil beds down the track. But where the track crosses viaducts and bridges, the sleepers can be fixed to metal and concrete structures. Small bumps can form in the track at the transition points between soft embankment and rigid bridge. These bumps won't derail the train, but at 300 kilometers per hour, they can make passengers very uncomfortable. Italo's reputation depends on giving everybody on board a comfortable ride through all stages of the journey. To beat the bumps, engineers build a two-layer solution into the train's bogies. Detaching a bogie from its carriage reveals the secret to a smooth ride. Layer 1. 4 24-centimeter long steel coil springs. Layer 2. A set of hydraulic piston dampeners mounted on the bogie's side. And a pair of bags made from tough rubber. These sit directly beneath the train's carriages. The layers work together to iron out jolts and shakes. The coil springs compress to absorb the impact of the bogie's wheels hitting bumps on the track. Pistons inside the hydraulic dampeners soak up jerky sideways movements to keep the train's wheels on the rails. The inflatable bags adjust the level of cushioning depending on the number of passengers on board the AGV. Thanks to its ingenious suspension, passengers on this train enjoy the most comfortable of rides. The silky smooth suspension allows Denis to keep his train close to maximum speed. He claws back the time lost stopping in Reggio Emilia. But up ahead lies a challenge that threatens to push the train behind schedule again. How does this super train blast through tunnels at 300 kilometers per hour without blowing its passengers' eardrums? And what stops its wheels spinning on the slippery track? The AGV is nearly halfway into its 600-kilometer journey from Milan to Rome. The train is right on schedule as it speeds passengers through the Apennine Mountains. Up front, driver Denis guides the train around bends at 300 kilometers per hour. Traveling this fast leaves little time to react if he needs to make an emergency stop. To keep both the driver and passengers safe in the event of a collision, engineers build an innovative protection system into the train.
This train can run up to 300 kilometers per hour, and in case of accident, you have to absorb a lot of energy.
The nose is this train's first line of defense. Inside are 3 layers of protection. A piston for absorbing extreme impacts at the front. Behind that, a steel plate with 5 crumple zones. And a crash-proof driver's cage made from high-density steel.
Driver feel very safe because in case of incident, this part is able to absorb all the energy and the driver cab is safe.
Crash tests show the safety system absorbs the impact of a truck traveling at 100 kilometers per hour, greatly increasing the driver's chances of surviving a crash. The AGV train is now deep in the Apennine Mountains. The fastest route through is via a series of 9 tunnels, some up to 19 kilometers long. Driving a train into a tunnel at high speed is a formidable engineering challenge. Air inside a tunnel is trapped within a confined space. When a train speeds into a tunnel at 300 kilometers per hour, it compresses the air inside. Like a piston, the front of the train pushes along a cushion of air. In a split second, the air pressure in the carriages behind drops rapidly, before the air rushes back milliseconds later. This sudden pressure change could damage the most pressure-sensitive part of the passengers' bodies, their eardrums, making their journey very painful. Guaranteeing passenger comfort is critical to maintaining Italo's reputation as a premier train service. To avoid ruptured ears, driver Dennis can, at the push of a button, deploy an ingenious sealing system built into this train. Hidden inside the roof of each AGV carriage, 2 high-powered fans draw in air, pressurizing the cabins. On the driver's command before entering a tunnel, flaps concealed in the roof snap shut over the fan intakes. Rubber seals inflate around the doors, making the carriage airtight, just like an airplane, protecting the passengers' eardrums from damaging changes in pressure. As the train nears the tunnel, Dennis activates the flaps. The train is now completely sealed. It enters this 19-kilometer-long tunnel at 300 kilometers per hour. The passengers feel nothing.
It's no problem to be in the tunnel when you travel on a train. I think it's quite the same as to be outside.
After exiting the tunnel, Dennis unseals the carriages. Clear of the Apennines, his train powers on. Within 10 minutes, he arrives at the next stop, Florence. For the onward journey, Dennis will pull out of the station the same way he came in. To do this, he must switch to the driver cab at the other end of the train. The clock is ticking. The train must leave on time. With all passengers finally aboard, Dennis kicks the train into gear and accelerates out of Florence station. The AGV has just 90 minutes to reach Rome. Dennis must push the train to the max. But the stresses and strains of the task increase the risk of mechanical failure. What makes this super train strong enough to stand up to extreme punishment? And what stops its polished steel wheels from spinning out of control? The AGV is nearly 400 kilometers into its 600-kilometer journey from Milan to Rome. The reputation of the train's operator, Italo, rests with the train arriving on time. Driver Dennis once again pushes his AGV up to its top operational speed of 300 kilometers per hour. So far, it has traveled flat out for most of its journey. The longer the train travels at its highest speeds, the greater the stress on its components. At the train's top speed, the AGV's wheels and axles turn at 1,800 RPM. This huge stress, together with the extreme heating caused by friction with the track, increases the risk they could shatter, potentially leading to disaster. The 20th of December, 1984. Fire erupts from a ventilation shaft connected to Summit Hill Rail Tunnel in the United Kingdom. The cause of the blaze, a freight train hauling 13 tankers carrying more than 1 million liters of vehicle fuel. A defective axle bearing on one of the tankers breaks. It causes the train to come off the tracks and all the tankers behind to derail. The fuel ignites, causing one of the largest tunnel fires in history. Luckily, no one is killed or seriously injured. To prevent such a disaster happening to the AGV, engineers design its wheels to soak up extreme punishment. Each of the train's 48 wheels is made from a single 1.2-ton piece of steel. During forging, each wheel is quenched in liquid. The exterior cools rapidly, creating a hard surface. The core cools slowly, making it more flexible. The wheel's softer insides absorb extreme shocks and stresses. The hard exterior can pound the track for over 1 million kilometers. The wheels and axles are tough, but they can develop microscopic fractures that weaken the metal to the point it breaks apart. Regular checkups are critical to identify potentially dangerous defects before it's too late. The cracks are too small to see with a human eye. So engineers use ultrasonic testing to look inside the metal.
Con questa macchina ultrasuoni noi riusciamo a capire se ci sono delle possibili indicazioni che ci indicano delle cricche sul materiale, quindi con possibili conseguenze disastrose per il servizio. Questa è un'attività che noi ripetiamo ogni 375.000 chilometri.
This scanner sends a sound wave into a train's axle. The strength of the sound's reflection alerts engineers if there's a dangerous defect hidden inside. The team immediately replace all damaged wheels and axles. Super tough wheels give Dennis the confidence to push on to Rome at top speed. The Italian capital is still 100 kilometers away, and the clock is ticking. Commuters on board expect to reach their destination in 30 minutes. But ahead lies a challenge that threatens to push the train behind schedule. hazards on the line itself. Mud, leaves, and other organic matter on the metal tracks can make them slippery, causing the AGV's wheels to lose grip. A lack of grip between the wheels and the track could turn into a skid. This could greatly increase the stopping distance of the train in an emergency. In the worst case, the skid could cause a train to come off the rails. To beat the skid, engineers build 4 special boxes into the nose of the train. Combined, they hold 80 kilograms of coarse sand. A pipe connects the box to an outlet directly in front of the lead wheels. At the press of a button, the train's driver can release the sand onto the track. When pushing hard to beat the clock, this simple system can make all the difference in slippery conditions. Sensors mounted in the bogies monitor the rotation of the wheels on each axle. If one axle spins faster than the others, it means one of the wheels is slipping. To prevent loss of traction, the driver releases sand onto the track to help give the wheels extra grip. The sand has a lot more friction than the steel rails. Although only a few millimeters deep, the sand layer breaks the erratic spin of the slipping wheel, bringing it back under control so that it regains traction. After nearly 550 kilometers, Rome Central Station is in sight. Dennis's AGV must arrive on schedule, but one final obstacle could wreck his chances. Up ahead, the train's specially built high-speed track crosses a network of suburban rail lines. What technology stops this super-fast train from getting stuck behind slow commuter services? And will this train make it to Rome on time? One of Europe's fastest passenger trains, the AGV, is now just 20 kilometers from its destination, Rome Central Station. But crisscrossing commuter lines make this the slowest section of the entire route. Operations Director Sofia Apadula monitors the train's progress from Italo's command center.
Approaching to Rome, trains leave the high-speed line and they travel on the same tracks where there are also local trains.
After speeding through Italy at 300 kilometers per hour, getting bogged down in this congestion on the outskirts of Rome will blow any chance the train has of reaching its destination on time. Sophia and her colleagues access a system called Communication-Based Train Control to monitor in real time the precise location of every Italo train in Italy. Its primary purpose is to tell an infrastructure manager the status of essential systems such as signals, electricity cables, and junctions. When it shows congestion lies ahead for time-critical services, Sophia can request the track be cleared of slower traffic.
Sometimes we have, like in this case, to move the train on that way. According to the rail infrastructure manager, we can pull this train out of the high-speed line before in order to get the train to the main station on time. Sì, il gestore mi dice che la linea è pulita e potete procedere. Siamo a posto. Grazie.
With the track ahead clear, Dennis's train has every chance of arriving on schedule.
with Italo, I must admit that the trains are always on time.
It's a very good service. I don't have any problem with so good experiences.
Finally, after 3 hours and 30 minutes, the train pulls into Rome station.
We've just arrived to Roma Termini. The train is on time. We've done a good job today.
The AGV's reputation for super speed and punctuality remains intact.
Siamo arrivati a Roma in orario. Io ho finito il turno, per adesso.
Today, Dennis's train accomplished its mission. It's all thanks to 5 engineering marvels built into its sleek frame that help make it one of the world's ultimate passenger trains. Intelligent electric motors maintain the train's speed up any incline. Reactive pantographs safely channel 25,000 volts from live overhead cables. Sophisticated multi-layered suspension smooths the ride. An ingenious pressurized sealing system protects passengers' eardrums. Sandboxes beat greasy track and stop wheels slipping. This is a train that's fast and engineered for both safety and passenger comfort. The Italo AGV is built to be the ultimate in its class. Towering 167 meters over Las Vegas. This is North America's largest observation wheel, the High Roller.
Because of building in Vegas, it requires you to build the biggest and the best.
Las Vegas's star attraction must keep turning and give the thousands of tourists who flock to this city the ride of their lives.
It's going to be a busy, busy night.
How did engineers build this mega wheel in the sky? And how does it deliver one of the most spectacular views in the world?
We wanted our guests to feel like they were floating in space.
We unlock the engineering secrets that help the High Roller wow the crowds. From its one-of-a-kind single rim to the ingenious capsules that stay perfectly level through every rotation, to reveal what it takes to build the ultimate mega wheel.
Welcome to Las Vegas!
With its bright lights, hotels and casinos, Sin City is famous the world over. 40 million tourists flock here every year to try their luck at the gambling tables, watch spectacular shows, and soak in the glitz and glamour. They spend close to $35 billion each year. Competition between hotel casinos vying to bag a bigger share of this revenue is fierce. They erect ever more spectacular attractions to draw in larger crowds. To stand out, Caesars Entertainment decided to build big. They constructed this. The Las Vegas High Roller. Costing $300 million, this megastructure now defines the Las Vegas skyline. It is built to a revolutionary design and requires a team of skilled mechanics to keep it moving. The wheel's objective is to reward intrepid passengers with unrivaled views of the city. The high roller is built with innovative technology hidden under the hood to help wow the crowds and give them the ride of their lives. "28 temperature-controlled, precisely geared capsules stay perfectly level all the way around. A unique single-rim design provides near unobstructed 360-degree vistas across Las Vegas. And a mighty hydraulic arm comes to the rescue if the power goes out. All these elements combine to make the high roller the ultimate observation wheel." General Manager Eric Eberhardt led the team tasked with making high roller a reality.
Because of building in Vegas, it requires you to build the biggest and the best and offer something the guests cannot experience anywhere else in the world. We really push our designers and engineers to create a world-class attraction that's unique and push the boundaries of observation wheels.
And this weekend promises to test this revolutionary wheel to the limit of its endurance. It's spring break. An estimated 800,000 people will descend on Vegas, looking for a good time. The wheel must complete 130 rotations, each taking 30 minutes, and carry thousands of people over the next 4 days, stopping for just 6 hours each night for critical maintenance. Breakdowns will dent Caesar's reputation and potentially drive away visitors eager to spend their dollars at the casino's gambling tables. The pressure is on. Thursday, 8 p.m. The long spring break weekend rush begins. High Roller's entrance hall fills with tourists eager to glimpse the wonder of Las Vegas at night.
I'm really super excited to see the hotels, the beauty of them, and all the lights of Vegas.
The first challenge for building a wheel this big: how to keep the 160-meter diameter frame rigid. Its narrow single rim doesn't look tough enough to support its 1,800-ton weight. High Roller's strength is the result of a groundbreaking innovation built into its DNA. 1893. Engineer George Ferris unveils the world's first great wheel at the Chicago World's Fair. To keep the wheel strong but lean, Ferris pioneers a spoke design that becomes the blueprint for almost all later wheels, including the High Roller. The cables hold up the bottom half of the rim. Their tension pulls the rim inwards. This allows the top half to support itself like the arch of a bridge. These two forces work together to keep the entire rim strong and rigid as the wheel rotates. But erecting a structure this tall and thin is a unique construction challenge. If engineers build High Roller from the bottom up, the cables support half the wheel's structure. But building the top half unsupported will overstress the rim and trigger a structural collapse. One solution is to support the wheel with a scaffold 167 meters tall. But scaffolding this high is unstable. Its footprint must cover a huge area to stop it from falling over. But this sprawl will encroach on neighboring roads and buildings. How do you build North America's tallest wheel without building the continent's largest scaffold? In the late 1990s, the engineers building the 135-meter tall London Eye used geography to solve the problem: the River Thames. They assembled the wheel horizontally on platforms in the river. Once the rim and spokes are complete, they lift the entire wheel into its vertical position. In Vegas, building high roller horizontally is impossible. The city has no river. Giant hotels and transport infrastructure surround the chosen construction site. Project manager Randy Prince must find the solution.
Logistically, this was a very challenging project. We've got two major hotels that had to remain in operation. We had to keep a roadway in operation because it was an emergency fire access throughout this entire project.
Randy's only option is to build high roller vertically, but with one critical modification. His team deploys an ingenious solution to stop the wheel from collapsing under its own weight as they build upwards. First, they fix a pair of 68-meter long metal struts to the wheel's central spindle. To this, they attach the first 16-meter long section of the rim and cable spokes. Next, powerful hydraulic jacks push this completed segment around by 13 degrees. Engineers then repeat the process, joining together more struts, rim sections, and cables. The rotating wheel stays rigid and stable as it grows segment by segment. Once all 28 rim sections are in place, engineers fit and tension the last of the wheel's 112 steel cables. They remove the struts one by one until the wheel supports its own weight on the central spindle.
When that last strut came out, I think it validated for all of us the designer's vision. There you had this purely circular form redefining the Vegas skyline. And we went, wow.
Today, the High Roller is a Las Vegas landmark, visible from anywhere in the city. On the first night of spring break, the High Roller carries thousands of people visiting Sin City for the long weekend. But a new day brings new challenges the super wheel must face. How does this monster machine beat damaging desert winds? And what is the engineering secret that gives the wheel spectacular, near unobstructed views? Friday morning in Las Vegas, the second day of the long spring break weekend. The High Roller spins over 1 million tourists each year, but passenger numbers surge during busy holidays. Everybody stepping aboard is a potential customer for Caesars Palace Hotel and Casino. The wheel must deliver the ride of their lives. These passengers are the latest in a long line of thrill seekers, eager to fly on ever larger mega wheels. In 1893, George Ferris's revolutionary 80-meter design triggers a race to build bigger. Over the next 100 years, observation wheels grow steadily larger. But it's not until the 21st century that they get really big. The 135-meter London Eye becomes the world's tallest wheel in the year 2000. 6 years later, this 160-meter wheel, called the Star of Nanchang, steals the crown, only to be beaten by 5 meters by this wheel, the Singapore Flyer, in 2008. The High Roller adds a further 3 meters to the world record, and it could have been even bigger.
We always wanted to make the High Roller the biggest and the best in the world. We were somewhat limited. The major international airport, McCarran, is less than 5 miles from here, so the Federal Aviation Administration limited the height that we could go to, so we took it right to the limit of 550 feet.
Size is just one objective for High Roller's designers. The bigger prize is to write engineering history. Build the first wheel in the world with near unobstructed 360-degree views from every capsule, at every point of rotation. All big observation wheels, from Ferris's original to the Singapore Flyer, are actually 2 wheels bolted together. 8-meter wide trusses join the 2 rims of the London Eye. This means for most of the rotation, the wheel's physical structure blocks passengers' sightlines from one side of the capsule. Only when a capsule reaches the very top do those inside enjoy an uninterrupted vista. To realize the dream of near unobstructed views, High Roller's engineers simply remove one entire rim and all the trusses.
So this is what the High Roller is all about. We eliminated most of the visual obtrusions and really give you the sensation of floating. And it gives you a full 360-degree view.
The effect is a big hit with Vegas's spring break vacationers. But building an observation wheel with just one rim potentially leaves it vulnerable to the forces of nature. The traditional 2-rim design of wheels, like the London Eye, makes their structure stiff. It's this stiffness that keeps these wheels rigid in strong winds. Removing one rim reduces rigidity. In strong winds, there's a big risk a single rim design could flex. The bending wheel could hit critical infrastructure and overstress its cables to the point where they snap and risk a catastrophic collapse. Las Vegas sits in a valley in the Mojave Desert. This geography leaves the city vulnerable to strong winds. High Roller's team monitors the speed of the wind from this dedicated control room.
Good. Can you pull up the weather so we can check it real quickly, please?
Sure.
Low wind speeds today, that's good. The days preceding this weekend, we had quite high wind gusts coming through the Las Vegas Valley. Some gusts were as high as 60 miles an hour.
In theory, winds this fast could fracture a single rim wheel and shatter the dream of engineering the illusion of floating on air. So to eliminate the natural flex in a single rim design, High Roller's engineers devise an ingenious solution. They extend the length of the central spindle to 30 meters, nearly 4 times the length of the spindle on the London Eye. This widens the angle from which the cables pull on the rim from either side, just like the guy ropes on a triangular tent. The longer central spindle makes the high roller as rigid in strong winds as a traditional double rim wheel design. The wheel stands firm in strong winds, but gusts still have the potential to ruin the experience for the thousands of tourists riding high roller this holiday weekend. Wind vibrates the tubular legs that support modern observation wheels. This movement can rock the rim, wobble the capsules, and make passengers nervous and seasick. Hidden inside the support legs is High Roller's secret for beating the shake and to guarantee a smooth ride every time.
Any sudden movement is going to detract from this experience of basically serenely floating in the air as you go around and look at Las Vegas. We needed to do whatever we could to make that experience as smooth as possible.
Engineers fit special devices called tuned mass dampeners to combat vibrations. Each of the 13 dampeners consists of a weight of up to 60 kilograms, suspended by cables, attached to tuned springs. Together, they counteract vibrations caused by wind to give passengers the sensation of floating on air. By 2 p.m. Friday, this windproof wheel has spun hundreds more spring break tourists high above Vegas and the Mojave Desert.
It's amazing. I mean, I did get the butterflies in the stomach a little bit, but it was definitely a nice experience.
I've gambled and lost a lot of money, and you enjoy some good food, but this is totally different than anything that I've done in Vegas.
As the sun sets on Sin City, Friday night promises to bring even larger crowds. How did engineers build this huge structure to fit in the middle of crowded real estate? And what is the secret for turning a 2,200-ton mega wheel? (8 p.m. Friday in Las Vegas. Tonight, High Roller must spin close to full capacity, carrying over 1,000 passengers every 30-minute rotation. It must keep turning to draw the crowds and drive business to Caesars Restaurants and Casino on one of the busiest weekends of the year. As darkness descends, Las Vegas lights up, and so does this city's big wheel. "2,000 LEDs cover High Roller in a chameleon cloak of light, turning the wheel into a beacon visible from anywhere in the city."
Obviously, Las Vegas is the city of lights, and there was no doubt that we had to put on a very special show when we opened up the High Roller. These two panels allow us to select from a color wheel of colors and allow us to set up the wheel for special events or just our normal operations.
High Roller also offers a special service to attract the spring break party crowd.
Yeah, we are officially at the time to meet the shot.
For a fee, visitors ride with a personal bartender and fully stocked bar.
Vodka soda, fresh glass.
At the halfway point in the spring break long weekend, this 167-meter tall wheel has completed 72 rotations and carried thousands of tourists. A wheel this high must stay perfectly vertical at all times to run smoothly. High Roller must have a rock-solid foundation, or there's a risk the mighty metal ring could topple over. Traditional wheels stand on A-frame structures angled outwards. They guarantee stability by spreading the wheel's weight over a bigger area and lowering the structure's center of gravity. But to build wide legs, you need space. And that's in short supply in this part of Vegas. High Roller's construction site is located in the middle of prime real estate. It sits in an area crammed with obstructions. A 19,000 square meter retail development. The intersection of two busy roads. And a section of Las Vegas's raised monorail. These obstacles restrict High Roller's engineers to a construction footprint of only 65 meters by 22 meters. The problem is, no matter how they orientate the High Roller, the giant wheel cannot fit on the site without hitting a building or standing in the middle of the road. Borrowing from previous designs is not an option. Other 21st century wheels like the London Eye and Singapore Flyer stand in less cluttered areas with space to stretch their legs. Engineers must devise a unique solution to fit High Roller inside its tiny footprint. They turn the wheel's legs to angle inward, so they touch the ground within a narrow 1,430 square meter area. The wheel is solid along its north-south axis, but its narrow stance makes it unstable along its east-west axis. Engineers build an ingenious fifth leg out from the central spindle to secure the wheel. It reaches over the neighboring road and touches down in a nearby car park. 5 points of contact with the ground gives High Roller perfect balance. Once workers complete its foundations in mid-2012, it takes another 2 years to finish the wheel's mighty structure.
In order to complete the High Roller on time and on budget, it had to be a very well choreographed operation.
We literally had parts and pieces coming from all over the world. Steel from China, glass from the cabins from Italy. We had to coordinate an enormous amount of material coming into this site, getting brought in just at the right time.
It takes 7,700 meters of cables, over 2,000 tons of steel tubes, 28 capsules, each weighing over 27 tons, and a workforce of 600 to construct the ultimate observation wheel.
Building anything on this scale is quite an endeavor and quite challenging, but it is also extremely rewarding.
When we finally get open, and you see thousands of people streaming by going ooh and ah, looking at the wheel saying what a wonderful thing it is, and you get the chance to say, you know, I was part of that, you go, wow, that was a pretty special thing.
By the end of Friday night, the super stable High Roller has spun thousands more spring break vacationers. But tomorrow promises to be the busiest day of the long weekend. What innovation will drive the 2,200-ton wheel non-stop for 16 hours? And what's the secret to keeping High Roller turning even when the power goes out? In Las Vegas, the High Roller has spun thousands of people over the first 48 hours of the spring break holiday. Passenger numbers can double at weekends, and this Saturday evening promises to be even busier. It falls to Operations Director Carolyn Gargiulo to ensure the wheel's ready to meet the demand.
It is a Saturday night, which is typically extremely busy for the high roller, and we have a private event on top of that, and then, of course, our general admission guests. It's going to be a busy, busy night. We will be stressed to our max and pushed to our limits.
Tonight, High Roller must spin close to 1,100 people every half-hour rotation. Driving the vertically mounted 2,200-ton mega wheel around and around non-stop is a huge engineering challenge. The center of the wheel is the obvious position for a motor, but rotating High Roller from its spindle is a recipe for disaster. The huge torque required to move the mega wheel could snap High Roller's cables. The solution is to power the wheel from its rim. This reduces the load on the cables. But the wrong propulsion system can destroy a big wheel's reputation. In 1895, engineer Walter Bassett opens this 94-meter tall Ferris wheel in London. Bassett's engineers fix a pair of 300-meter long chains around the rims to turn the wheel. A pair of underground steam engines pull the chains. 2 5-ton weights keep them taut. In July 1895, a weight breaks loose. An 8-ton chain falls slack and jams between the rim and one of the carriages. The wheel comes to a grinding halt. Trapped passengers wait 7 hours for the chain to be repaired and for the wheel to start moving again. In Las Vegas, engineers deploy a rugged propulsion system to keep High Roller turning big passenger numbers. 8 units fitted with 4 large truck tires, pinch shafts attached to both sides of the rim. A 95-kilowatt electric motor powers each tire unit to drive the wheel around. It's critical the system works flawlessly to cope with increased demand during this spring break weekend.
Reliability is key for this attraction. One of the critical elements in maintaining this reliability is the maintenance that has to take place every night, 365 days a year.
From 2 a.m. each morning, the wheel closes and High Roller's dedicated maintenance team gets busy. Senior mechanic David Pinkerton must ensure the tires and motors are in perfect condition.
When we're checking the tires, we're looking for cracks, we're looking for bubbles, we're looking for low tread, we're looking for low tire pressure. All right, Josh, let off a little bit. Looks good there, Josh.
David and his team must find faults during this downtime. Failing tires while the wheel is running could knock High Roller out of service and seriously dent its reputation.
So it's all done, all the tires are good? Yep, we're clear.
With the tires ready to roll, next the team checks the motors. If any of them fail, the big wheel has built-in redundancy to keep turning at its normal speed of 30 centimeters per second.
We run with all 8 drive units at one time. We could operate with 6 drive units. If we lose 2 more drive units after that, then we're in half speed.
High Roller's engineers also build in a backup generator to keep the motors running if the electricity switches off. But there's always the risk a freak event could cut both electric and diesel power and bring the big wheel to a grinding halt. In the unlikely event the High Roller loses all power, it can fall back on an ingenious failsafe. 2 independent diesel motors power a pair of 3.3-meter-long hydraulic arms. The front arms grip the wheel's rim and push it around. At the same time, two back arms extend, grip the rim and pull the wheel. Repeating the sequence rotates the wheel smoothly. Using this system, workers can rescue all High Roller's passengers in just 2 hours.
This is the last chance that we have to get people down. We won't use this unless we lose power to everything.
David and his team must test the system to be sure it'll work in the worst-case scenario. The hydraulically powered arms spring into action. They grab the wheel and pull it round. The system works without a hitch. Saturday night of the long spring break weekend, the party is in full swing.
5 minutes left, guys, 5 minutes!
High Roller is going strong. 24 hours remain of the holiday weekend. To keep wowing the crowds, the wheel must deliver a spectacular experience every ride. What ingenious technologies help the capsule stay perfectly level at every point of High Roller's rotation? And how does the wheel keep thousands of passengers cool in the searing desert heat? (10 a.m. Sunday), the last day of the long spring break weekend. Eager tourists line up for Las Vegas's star attraction, the High Roller. Over the next 15 hours, it must fly thousands more people above the city's world-famous skyline. The temperature this morning is a balmy 25 degrees Celsius. Ensuring this wheel can survive Las Vegas's extreme climate is a huge challenge for High Roller's engineers. In spring, the mercury can top 34 degrees. If made from regular glass, temperatures this hot will turn the High Roller's 28 capsules into mini greenhouses, frying their occupants. So the wheel's designers build in the ultimate see-through barrier to beat the heat. A special coating reduces the penetration of the sun's energy into the capsules. Handmade double-paned glass stops heat radiation from passing into the interior. In a closed capsule, the air temperature is also critical.
All right, Josh, that's good. I'm gonna run up and grab the level.
Every night during High Roller's downtime, David's maintenance team test each capsule's air conditioning unit to make sure it pushes out air at a comfortable 23 degrees Celsius.
Air conditioning in Las Vegas, it's a necessary thing you have to have. You can't live without air conditioning in Las Vegas. The AC units, we change the filters and make sure they stay clean, because if the filters start getting clogged up, the airflow's not where it should be, and it'll make it get really hot in a cabin.
Batteries hooked up to each AC unit guarantee every capsule up to 6 hours of cool air if the mains power supply cuts out. Climate control ensures passengers enjoy a pleasant ride. Another challenge facing the wheel's engineers is how to create the sensation of floating serenely through the sky. It's critical the capsules stay perfectly level at every point of the High Roller's rotation. The cabins on early Ferris wheels hang from axles attached to the rim. These pivots rely on gravity to keep the cabins level. But this design makes for a rocky ride. Traditional cabins move freely about the axles that suspend them from the wheel's frame. This leaves the passengers inside vulnerable to feeling every bump caused by the wheel's turning mechanism, and puts the cabins at the mercy of strong winds. Both factors reduce passenger comfort. Worse still, for most of the ride, the structure of the wheel itself interrupts the view from the cabins. To solve these problems, High Roller's designers take gravity out of the equation. They use support struts called V-legs to fix each capsule to the outside of the rim. But doing this has the potential to jeopardize the passenger experience. Fixed capsules will turn upside down as the wheel revolves through 360 degrees. To solve the problem, engineers grip each capsule with an ingenious gear system. As the high roller spins in one direction, the wheel's capsules must rotate in the opposite direction to stay level. To turn precisely the correct amount relative to the big wheel, engineers fit each capsule with a toothed 5.3-meter diameter ring. An attachment arm connects the ring to a cog. As the wheel rotates, the cog's teeth turn the capsule's ring. This makes sure every capsule stays level, no matter where it is on the wheel. The system means engineers can mount the capsules on the wheel's exterior. This guarantees passengers experience spectacular, uninterrupted views of Las Vegas.
One of the best ways to find out if you're actually moving or turning is to watch the relationship to the V-leg. Here the V-leg is holding us by the side. When we first loaded, it was supporting us from the top, and when we were at the top of the ride, we were actually sitting on top of the V-leg. So as you're making your trip around, not only is the cabin doing a 360-degree turn, the wheel and the rim itself is doing a 360-degree turn.
Every year, High Roller spins over 1 million visitors above Sin City. Inside its perfectly level, temperature-controlled capsules. 1 p.m. Sunday. The long spring break weekend is almost finished. Over the past 60 hours, the 2,200-ton wheel has completed over 100 full rotations. With a late passenger surge expected this evening, it can't afford to break down now. What near frictionless engineering keeps this mega wheel turning? And what stops damaging desert sand from bringing it to a grinding halt? Sunday afternoon in Las Vegas. The spring break long weekend is almost over. In the last 72 hours, the mighty High Roller wheel has spun thousands of tourists over Sin City. Rotating around its 30-meter long spindle continuously for 16 hours is an epic engineering feat for an observation wheel this large. The rim, capsules, cables and hub weigh 2,200 tons, equivalent to 15 blue whales. This much weight turning on the spindle creates massive friction. Metal grinding on metal risks catastrophic mechanical breakdown. It's critical the moving metal parts slip past each other with as little friction as possible. In early 2013, engineers install a pair of 2.3-meter diameter roller bearings. Each one locks 60 free-moving roller elements within 2 steel rings. They seal the 9-ton bearings inside the 5-meter tall steel cable anchors. A giant crane lifts each one 80 meters off the ground to their final positions on the support legs. The installation of the bearings, hub, and spindle takes 2 months. The high roller's desert location creates a major problem for machines with big moving parts. Strong winds blow sand and dust across Las Vegas. If these abrasive particles build up inside the roller bearings, they will damage the precisely engineered metal components, and the wheel could come to a grinding halt. Mechanic Brian Arellanos is responsible for keeping the mighty bearings dirt-free. During crucial maintenance shifts, Brian and a co-worker ascend 270 ladder steps into the very heart of the wheel.
Right now we're actually inside of the hub of the high roller. This is the static spindle that stays still. On the other side of this seal is the bearing itself that's connected to the hub. And if the wheel were to be moving right now, we'd be rotating with the hub itself.
High roller's secret to beating the grit is grease. Lots of it. Pumps inject 1 kilogram of lubrication grease every day into the sealed housing containing the roller bearings. This constant flow of grease flushes out any particles that could grind the metal components. If the oozing grease contains foreign particles, Brian knows the roller bearing seal is broken and needs fixing.
All around us is the bearing, and this system right here is where our grease pump pumps the grease into, and this is where the excess grease gets flushed out.
The team regularly sends samples of grease to a laboratory for inspection under the microscope. But Brian is the first line of defense.
We do check it every week, and if we could see something with our naked eye, we know there's an issue with the high roller. We don't see any kind of foreign material in there, we don't see any air pockets, and overall it looks pretty good.
"5 p.m., Sunday. More eager riders stream aboard High Roller. The mighty wheel is on its final leg of this epic spring break long weekend. By the end of the day, this ultimate mega wheel has completed nearly 130 rotations and flown thousands of passengers over Las Vegas. Mission accomplished.
We had a very successful weekend thanks to our team. Because we were fortunate enough to create a Las Vegas icon, now the pressure is on us to make sure we maintain it and continue to operate for the next 50+ years.
High Roller soars higher, works harder, and carries more passengers than any other wheel in North America. Built into its huge frame are a series of engineering marvels that make it the pinnacle of observation wheel design. Innovative building techniques make construction possible within a crowded landscape. The unique support frame anchors the mighty structure to a tiny footprint. The one-of-a-kind single-rim design stays rigid in the strong desert winds. A diesel-powered hydraulic arm keeps the wheel turning if the electricity fails. Precisely geared, temperature-controlled capsules stay perfectly level around every rotation. This is a wheel that is big, gives its passengers an unrivaled field of view, and is now a landmark in one of the United States' most recognizable cities. The High Roller, built to be the ultimate mega wheel. It climbs nearly 50 meters into the air, then drops 90 degrees straight down at over 100 kilometers per hour. Valkyria is Europe's tallest dive coaster. What makes this ride so terrifying? And what keeps its trains locked to the rails through death-defying turns and head-spinning inversions?
It's our ambition to deliver the most exciting ride experience possible.
We unlock the engineering secrets of how this ride delivers big thrills. From the supersized structures that anchor it to the bedrock 25 meters into the Earth, to the space-age wheels that keep its trains rolling all season long, to reveal what it takes to build the ultimate super coaster. This is Liseberg Amusement Park in Sweden. 3 million visitors flock here every year to experience the park's 39 exciting rides and attractions. Competition is fierce between the hundreds of amusement parks across Europe. Liseberg's survival depends on attracting thrill seekers with newer, bigger and scarier roller coasters. To stay ahead of the curve, the park built this. Valkyria. This ride gets its name from the flying maidens of Norse mythology. Legend says they swooped from the sky and carried slain warriors to heaven. This coaster gives its passengers their very own Ride of the Valkyries. It is a dive coaster that drops riders 90 degrees straight down at 105 kilometers an hour into a tunnel and through a series of head-spinning inversions. At 47 meters high, Valkyria is the tallest dive coaster in Europe. Its aim is to deliver eager thrill seekers a heart-stopping ride up to 675 times a day. Valkyria is built with innovative technologies hidden under the hood to help it achieve its mission and wow the crowds. Mighty chains pull the coaster nearly 50 meters up into the sky and hold it at the top of the drop. Tough nylon wheels keep the train rolling to the end of the track. Super strong hydraulic harnesses keep passengers firmly in their seats. All these elements combine to make Valkyria the ultimate dive coaster. The next 48 hours promise to test the ride to its limits. This April weekend, Liseberg opens for the season. An estimated 20,000 people will pack this park to experience all the fun of the fair. Valkyria must operate close to full capacity, non-stop, for 8 hours a day. To add to the pressure, representatives of Europe's largest coaster club are in town to ride Valkyria for the first time. Their opinion counts, as it could affect the ride's popularity and future passenger numbers. Liseberg closes between January and late April, when temperatures drop to their lowest. The park mothballs its rides to protect them from the harsh winter weather. Engineers must test all of Valkyria's components to make sure they're in full working order before the season starts. Liseberg CEO Andreas Andersson must ensure the park is ready for opening day.
We have to disassemble the ride, we have to do all the annual maintenance, we have to make sure that the ride is in mint condition. There's a lot of work that has to be done to make sure they can reopen again in April.
7 a.m. The park opens to the public in 8 hours. It rests on the shoulders of technical manager Niklas Karlgren to perform the last-minute checks before Valkyria receives its first passengers of the season. Niklas's first job is to inspect every centimeter of Valkyria's 750-meter-long track.
I'm looking at the track-to-track connections for loose nuts and bolts. I check the column connections also for loose nuts and bolts. I look at the track, the screws. I look so there's always a straight line, so nothing has moved. Because we want to find anything that could become a catastrophe.
Next, Niklas must test the track's strength under operational conditions. He uses 18 water dummies to simulate the weight of a full ride.
Each of these weight is 75 kilo when it's filled up. It's a normal weight of a person, most of them now.
There's good reason for the dummies to take the first plunge. Europe's longest dive coaster plummets 50 meters into a subterranean hole. At the bottom of the vertical drop, the passengers are traveling at 105 kilometers per hour. Within the space of 40 meters, the track levels out and curves upwards out of the tunnel. The force the falling train exerts on this section of track is roughly equivalent to dropping an 18-ton weight on the rails. The track could fracture if it's not firmly secured to the ground, leading to potentially disastrous consequences. Valkyria needs a rock-solid footing. So the team at Liseberg work with David Norian to engineer a rugged solution.
The force of the train coming down to the tunnel is very high, so the foundations have to be attached to the bedrock underneath.
But reaching solid stone is a big challenge in this part of Sweden. When engineers start the build in 2016, they find 25 meters of thick clay lies between them and the bedrock. Diggers battle for 2 months to remove nearly 4,000 tons of mud for the tunnel. And when deeper drilled holes for the foundations do strike rock, the team discovers another problem. The bedrock slopes towards a nearby river. How can engineers anchor Valkyria to rock that changes in depth from place to place? To be sure Valkyria's foundations reach far enough into the ground, engineers drill 12 25-meter-long steel towers called piles into the bedrock. They pour concrete platforms on top of the piles. Engineers then fit the sections of coaster track to the concrete. Thick bolts create super strong joints between the metalwork. Together, the long piles, concrete and bolts lock the track into place. They make it strong enough to withstand the impact of Valkyria's train carriages, plummeting into the tunnel up to 675 times a day.
Valkyria is the bird's biggest project ever. It took hundreds of hours to complete this, and no matter which weather it was. Today I'm very proud that Valkyria sits here, but during the process it was very challenging.
2 p.m. The park opens to the public in just 1 hour. It's time for Niklas to test the track using 18 water dummies. He activates the 150-meter long lift chain. This pulls the train to the top of the hill. Moments later, it's poised for the drop. The track holds firm for the dummy test. But before he passes Valkyria fit for service, Niklas must ride the coaster alone.
Dummy test run went very well, but before I sign it off, I want to go a test run myself and see so everything sounds and looks good.
Any unusual bumps or scrapes will alert Niklas to potential mechanical problems. If he thinks they're serious, the ride can't open until they're fixed.
The first connection with the lift chain felt really good. Now comes the drop. As perfect as it could be.
The coaster passes the test with flying colors.
That felt really, really good, and it sounded nice, felt super good, so I'm ready to sign this off.
3 p.m. Liseberg opens for the season. The rush begins. Hundreds of visitors head straight for Valkyria. As demand increases, so does the pressure on Europe's tallest dive coaster. What are the engineering secrets that allow Valkyria to hold and then drop hundreds of passengers every hour? And how does this coaster spin and twist thrill seekers without coming off the rails? – 4 p.m. Liseberg Amusement Park's opening day of the season. Over the next 48 hours, the Valkyria dive coaster must give an estimated 20,000 visitors the ride of their lives. For decades, amusement parks around the world have competed to build bigger, better, and even more terrifying rides. 1989. The world's tallest roller coaster stands 62 meters high. 16 years later, the record more than doubles to 139 meters. In 1976, 3 inversions or upside-down rolls is the max. By 2013, the record quadruples to 14 loops. Valkyria's most iconic feature is its huge drop. One of the longest vertical drops in Europe. Nearly 50 meters, straight down. This ultimate dive coaster was engineered here, in this specialist metalworks in the United States. At Claremont Steel Fabricators in Cincinnati, a team of 80 workers bend, twist, and weld steel to make some of the greatest rides in the world. The factory covers an area the size of 73 tennis courts. Company president Bob Mampey drives the operation.
A lot of people can design roller coasters, but it's really difficult to execute the design, and that's what we do here, is execute the design.
takes 90 days for workers to cut 227 tons of steel to make Valkyria's 100 support columns. They mold the coaster's 77 individual track sections following a detailed blueprint.
Precision is the key to the game here. We produce these roller coasters to give the smoothest ride possible. Every millimeter counts.
Each track section receives 4 coats of special paints to prevent the salty air of Liseberg's coastal location from corroding the metal track. In 2017, heavy haulage experts start shipping Valkyria's 174 pieces of track and supports to Sweden. Engineers at Liseberg spend 1 year driving piles, erecting the support columns, and fixing the track sections into place. The passengers filling Valkyria's departure hall are the latest in a long line of thrill seekers eager to experience this next step in coaster evolution. Lifting 6 tons of train and passengers nearly 50 meters into the air is a huge challenge. The engineers who built this super coaster design an ingenious solution to literally pull the train up the hill without it ever slipping back. A continuous 150-meter long lift chain powered by a 230 kilowatt electric motor runs the length of the 45-degree incline. A metal pin mounted beneath the front of the train hooks into the lift chain. If a malfunction makes the chain fall slack, sprung metal blocks on each carriage lock into a toothed rail on the track, so the train can never roll backwards out of control. Rounding the hill's summit is just the start. Next, this extraordinary machine must suspend the train over the edge just long enough to terrify the passengers, before dropping them straight down into the tunnel. Building a system with the strength to hold 6 tons of train and passengers is a formidable engineering feat. Traditional mechanical brakes use electrically controlled calipers to grip metal discs attached to the axle. But stopping and suspending the coaster train plus passengers up to 675 times a day could cause extreme wear on brake discs like these. There's a risk that the brakes will fail and Valkyria's train will roll over the edge of the drop. Even worse, if there's a power cut while the brakes are on, the train and passengers could be stuck facing downwards, making rescue almost impossible. The 13th of April, 2017. The Joker's Jinx roller coaster at Six Flags America breaks down. One of the wheels jams on the track with the train 30 meters off the ground. Rescuers work for over 3 hours to get all 24 passengers safely off the ride. A mechanical breakdown like this on opening weekend will seriously dent Valkyria's reputation. The coaster's engineers build into the machine a rugged 2-stage system to hold it over the drop hundreds of times a day. Stage 1. Reduce the train's speed. To do this, engineers fix magnets to its undercarriage. Then they install metal plates at the top of the drop that interact with the magnets.
First thing that happens here before the drop is this magnetic brakes, and they will reduce the speed of the train. Yeah. Looking good.
At the hill's summit, the train disengages the lift chain. Motorized wheels on the track propel the train around a curve, before the magnetic brakes slow it to 7.2 kilometers per hour. Next comes stage 2. Dangle the train over the edge. Engineers equip Valkyria with a 20-meter-long drop chain system to secure the carriages in position.
So here we have the drop chain. The train hooks up into this chain, and the electrical motor will reduce the speed and actually electrical-wise hold it and give it a complete stop over this edge.
Hooks mounted on the train's undercarriage mesh with the drop chain. The chain connects to a 308 horsepower motor mounted under the track at the top of the ride. The motor slowly pulls the carriages over the edge. When the whole train reaches precisely the right point, the motor locks the carriages in place. Suspended in mid-air, the passenger's anticipation builds. Then the drop chain releases, the undercarriage pins fall free, and the train plummets straight down, reaching a top speed of 105 kilometers per hour. The drop chain will go slack if the ride's power fails, allowing the coaster train to fall freely, so it can never get stuck on the edge and trigger a complex and time-consuming rescue operation. 2 hours into the opening weekend, and Valkyria's big drop continues to wow the crowds. But this coaster must offer even more to earn ultimate status. What innovative engineering allows this machine to spin passengers 360 degrees without causing them to black out? And what technology makes it possible for a coaster with no engine to roll right around the track? In Sweden, it's the season opening weekend at Liseberg Amusement Park. Eager thrill seekers queue for the biggest, scariest rides. Top of their list, Europe's tallest dive coaster, Valkyria. Their experience starts long before they step aboard. Inside the departure hall, swords, shields, and fiery cauldrons evoke the theme of some of Norse mythology's most famous characters.
Valkyries are these goddesses that pick up slain soldiers on the battleground, and they are flying through the air, diving down, picking up these soldiers and bringing them to Valhalla, the Viking version of heaven.
By the time passengers climb aboard the train, they're ready for their very own ride of the Valkyries.
It's a really good choice on the theming on a roller coaster, and the name Valkyria goes really well with it. It raises the expectations and the overall feeling you get when you ride.
Valkyria drops thrill seekers 50 meters into a subterranean tunnel. But to qualify as the ultimate in its class, this coaster must do more than just fall vertically.
A good ride is actually almost like a good film. It has a beginning, it has a build-up, it has a climax, and then it sort of fades out. And I think that Valkyria does just that.
To make Valkyria a white-knuckle ride the whole way around, its designers build in 3 circular loops called inversions. These give passengers the buzz of turning upside down. But history proves there's a fine line between thrilling riders and seriously injuring them. 1895. America's first roller coaster with an inversion opens at Coney Island. The Flip-Flap Railway features a small diameter circular loop. Many passengers complain of whiplash and other injuries following their ride. The Flip-Flap's problem is that its loop is a perfect circle with a tight 3.8-meter radius. The train must travel more than 22 kilometers per hour to make it around this full loop. The acceleration this generates subjects passengers riding the train to 12 Gs of force. That's equivalent to 4 times the force astronauts feel during a rocket launch. The Flip-Flap's bad reputation spreads. A greater number of spectators turn up to watch unwitting passengers suffer injury than thrill-seekers wanting to ride. The Flip-Flap is dismantled after 7 years. Valkyria's engineers build into the coaster a special loop with a twist to solve the problem of inversions with excessive G-force. Its design is named after the aerial acrobatics of a German World War I fighter ace. Max Immelmann pioneers a loop that tightens as his plane ascends and finishes in a roll. The maneuver keeps the G-forces low and helps him get the jump on his opponents. Valkyria's rails guide the coaster's train along the same path to curve upwards and simultaneously roll through 180 degrees. Valkyria's Immelmann twists at the top of the curve, sending the train out right side up. Passengers experience the thrill of an inversion without the extreme acceleration of a full loop. And their bodies are subjected to a comfortable 3.5 G of force. But one Immelmann loop is not enough to qualify Valkyria as an ultimate coaster. To take the ride to the next level, designers build in a set of wicked twists to spin passengers 360 degrees as they travel forwards at high speed. But rotating riders quickly without making them feel sick is another huge engineering challenge. Some radical coasters put the trains on the outside of the track. This twists passengers fast through a large circle, making their heads spin. The motion can make riders feel unwell by affecting the delicate mechanisms in their ears. Ill passengers on opening weekend will dent Valkyria's reputation and spell disaster for Liseberg. So her designers place the train on the inside of the curve to make the ride more comfortable. The simple switch spins the riders slower in a smaller circle centered around their chests. This reduces both head spin and the risk of sickness. Valkyria's twists and spins prove a big hit with thrill-seeking visitors.
You have the drop, which obviously is awesome on all dive coasters, but in Valkyria's case, it continues to deliver the whole circuits.
You get to get adrenaline rush, and then you can enjoy the ride, riding on the adrenaline for a few seconds more, and I love it.
By the halfway point in the season opening weekend, Valkyria has flown thousands of riders. And tomorrow promises to be even busier. What is this coaster's secret for keeping its wheels rolling no matter the weather? And what technology guarantees all passengers stay firmly in their seats? In Sweden, it's the season opening weekend at Liseberg Amusement Park. one attraction is a must-ride. Valkyria, Europe's tallest dive coaster, named after the legendary Norse maidens who swooped from the heavens. It drops 18 passengers down a 90-degree, 50-meter-long slope into a dark tunnel before flying through a series of wild inversions. Today, it must operate continuously for the next 8 hours to satisfy the long line of eager thrill-seekers. It's critical the train makes it all the way around the track every time it runs. Valkyria's trains have no onboard engines. All of their energy must come from the 50-meter fall at the start of the ride. Too much friction between the wheel bearings and axles will slow the trains down. Making sure the limited energy the coaster trains do have is channeled into keeping them moving forwards is a big engineering challenge. Every night, Valkyria closes. In the coaster's maintenance hangar, a dedicated team uses thick grease to lubricate all the coaster train's moving components.
Grease is a really important part of the operations here. The main purpose is to lower the friction between metal surfaces, and because of it lowers the friction, the wear also reduces.
But in this part of Sweden, the climate creates a big problem for greased machines. Temperatures in the early and late season often struggle to pass 10 degrees centigrade. At such low temperatures, the grease lubricating the wheels is thick and viscous. This creates drag inside each wheel and slows them down. The train loses speed, increasing the risk it won't have enough forward momentum to make it back to the station. The train could stop on the track, leaving the riders stranded. Engineers would have to manually drag the train back to the station, a job that could take hours.
So that's why a roller coaster train stuck somewhere on the track is one of my worst nightmares.
To solve the problem, engineers must reduce friction between the train's wheels and the rails. The 6 mounts on each train chassis hold pairs of 3 different types of wheel. Road wheels bear the train's weight. Side wheels control lateral movement. Upstop wheels positioned under the rail prevent the train from lifting away from the track. The harder the material, the lower its friction. Some coasters use super dense solid steel wheels. Their ultra-low friction keeps the train rolling to the end of the line. But steel wheels can make some coasters noisy, and their hardness can make riders feel every bump in the track. Valkyria's reputation as an ultimate coaster rests on giving every passenger a smooth ride. Engineers must balance comfort with the need for the train to complete the track after every drop, all season long. Their solution is to arm Valkyria with 2 different sets of wheels, one soft, one hard. Engineers' first choice of train wheels are made from polyurethane. These soft wheels give passengers the quietest, smoothest ride possible. But their sponginess increases friction, fractionally slowing the train. When thicker axle grease increases drag in cold temperatures, engineers swap the polyurethane wheels for a harder nylon set. Their tougher surface results in a noisier ride, but reduces friction, cancelling out the drag caused by the thick grease, so the train completes the track every time. Valkyria's super wheels keep its trains moving, and the thril's coming for thousands of white-knuckled riders. Demand to ride Valkyria skyrockets as the opening weekend ramps up. To complete its mission, the coaster must fly every passenger around the track safely and securely. What hidden technology keeps every rider firmly in their seat? And what will be the coaster enthusiast's verdict after riding Valkyria for the very first time? In Sweden, eager thrill seekers soak up the last few hours of Liseberg Amusement Park's season opening weekend. Europe's tallest dive coaster, Valkyria, is the star attraction. To qualify as the ultimate, this ride must both thrill its passengers and protect them.
Safety is a non-negotiable. We never, ever compromise when it comes to the safety of our guests.
The challenge for the designers of a coaster that drops, inverts, and spins its riders is how to keep everybody firmly in their seats all the way around the track. The solution is built into the restraints fitted to each of Valkyria's 18 seats. A pair of hydraulic cylinders squeezes liquid through one-way valves. These lock the padded shoulder restraints in place. A hydro valve makes sure the liquid's pressure stays constant to secure thrill seekers of every weight. The system intelligently adjusts its locked position to accommodate both adult and teenage riders. Once the ride is over, the one-way valves open and release the hydraulic fluid. Each week, Valkyria's maintenance team tests every restraint. They use a pneumatic gauge to measure the tiniest movement of each bar in the locked position. Mechanics replace immediately any restraint that moves by more than 2 millimeters.
The roller coaster is actually extremely safe. Your body thinks it's in danger, but it really isn't. These engineering marvels, these constructions are designed not just around thrill, but designed around safety.
Valkyria's engineers can rely on the super strong restraint system to keep riders in their seats. But Liseberg's geography presents another big safety challenge. It rains here for an average of 14 days every month during the 8 months Liseberg is open. And the amusement park sits in a river valley. This is bad news for one section of Valkyria's track. Valkyria's 3-meter deep tunnel sits just below the area's water table. After heavy rainfall, it's possible that water could seep through the bedrock and gradually build up inside the tunnel, to the point it laps over Valkyria's track. If that were to happen, when a train passes through the tunnel, the water could drag on the wheels, slowing the carriage. There's a chance the train wouldn't complete the rise out of the tunnel and would roll backwards into the dark, wet subterranean hole. Passengers stuck in water underground will seriously dent Valkyria's reputation and drive away thrill seekers. To make sure this never happens, engineers equip the ride with sensors. These monitor the water level inside the tunnel. The amusement park team receives an alert if the sensors detect pooling water. A pair of pumps then remove water from the tunnel long before its level could pose a risk to the ride's operation. Three hours to go until the season opening weekend rush is over. Valkyria has flown thousands of people and more wait in line for the ride of their lives. One of them is president of the European Coaster Club, Justin Garvanovich. Today, he and his club members will ride and review Liseberg's new coaster.
It looks impressive. It looks hugely impressive, and huge being the right word, I think. It's Europe's tallest dive coaster as well. It's about 200 feet above the ground over there, and it dives below those, so the drop's substantially bigger. I can't wait.
Justin is a veteran of over 2,000 coasters with nearly 100,000 rides under his belt. His opinion could make the difference between Valkyria joining the ranks of ultimate rides and falling to the bottom of the popularity table. What will be the verdict? And what technology promises to be the next leap forward in coaster design? Liseberg Amusement Park's busy opening weekend is almost over. Valkyria is the latest in a long line of pioneering coasters, pushing the limits of speed and exhilaration. In a fiercely competitive industry, the challenge for engineers is how to make their ride stand out. Liseberg's solution is to build a virtual reality Valkyria that passengers can ride before they climb aboard the real thing. The park reaches out to Simon Jimifors to develop this experience. His expert team uses 3D modeling to build around Valkyria's track, a mythological world of heroes and fantasy creatures.
We were super excited because it's so fun project. We got to build a roller coaster and have it here in the office, of course. They have the real track in 3D. We just need to build something around it. Falling rocks and some monsters and fire and everything cool.
Wearable technology plunges the passengers into the world's sights and sounds. A motor-driven chair replicates the sensation of riding the real Valkyria. The virtual ride goes live in 2017. Its unique mythology-inspired theme wows thrill seekers. It's possible the next evolution will allow passengers to experience the virtual world at the same time as riding a real-world coaster.
I'm really excited about the future. When the VR tech is more responsive and immersive, we have a chance to create that world. We've only seen the beginning of the use of virtual reality in amusement parks. It's going to be huge.
6 p.m. Liseberg's busy opening weekend will draw to a close in 5 hours' time. President of the European Coaster Club, Justin Garvanovich, is here to ride Valkyria for the first time. Liseberg CEO Andreas needs him to experience the ride of his life.
For every guest walking through the gates, we want to create unforgettable experiences. We want to create, the best day of the year.
But Justin isn't just any guest. His coaster reviews really count. Valkyria must receive 5 stars to join the ranks of ultimate rides. Now is the moment of truth.
You never know where we're going to go.
wonderful. The drop worked perfectly, absolutely fantastic. Can we go again, please?
Justin delivers his verdict to park boss Andreas.
I loved it.
Oh,
it does,
good.
Scares you, it worries you, it thrills you. It wants you to get back on again.
Oh, yeah,
it is
yeah.
as smooth as glass.
Yeah, it is, it is. I think, you know, for the location we're in, being a very compact city-based park, I think this is perfection.
Liseberg's busy opening weekend ends on a big high. The park's star ride completes its mission. Valkyria has flown thousands of visitors over the past 48 hours and cemented its reputation as a premier amusement attraction.
We really liked the dive coaster concept, but we wanted to take it further. We really wanted to build the ultimate compact dive coaster for the European market, and I think we succeeded.
It's all thanks to a series of engineering innovations built into the twisting body of this machine that helps make it one of the world's ultimate rides. Deep-sunk, super-strong piles secure precision-engineered tracks to the bedrock. A mighty drop chain holds the coaster on the edge. Near frictionless wheels keep the coaster train rolling right around the track. Head-spinning inversions and corkscrew twists exhilarate passengers. Hydraulic harnesses keep everyone firmly in their seats. This is Europe's tallest dive coaster and one of the most thrilling rides in the world. Valkyria is built to be the ultimate in its class.